Hello, my name is Bob Ward from the Microsoft Corporation. What you're about to watch is a recording of a talk I did at this year's past summit called Inside SQL OS. I've had a reputation at several past summits for doing very technical sessions, and this is probably the most technical session I've ever done. I want to make sure before you watch this that you understand there's full credit needed to other people that produced this talk, including the SQL OS team and other CSS colleagues that I work with in Microsoft. Now, unfortunately, due to technical difficulties, the first 13 slides of this recording of my talk were not properly recorded. The good news is that the majority of these slides cover basic operating system principles, and it's information you can see when you download the PowerPoint deck. So the recording you're about to watch actually starts on slide 14, where I introduced the architecture of SQL OS and really contains the starting place of the meat of the talk. In addition, on slide 18, one part of a demo I did using the Windows Debugger was actually also not recorded. But there are other demonstrations in the talk where I used the Windows Debugger. I'm sorry for any difficulty this may have caused you as you go through this talk. And as you go through this session, and you look at those slides that were not recorded in the talk, or any other slide you hear in the recording, and if you have questions about them you'd like to ask me, feel free to send me an email at bobward@microsoft.com, and I'll be happy to entertain a discussion with you about this topic. I hope you enjoy this session. It's very fast-paced, so I'm sure you'll need to watch it many different times to understand some of the concepts, but I think you'll find the information that I'm going to provide very useful for you to understanding how SQL OS is the engine that powers SQL Server. Thank you. It is not a Windows service or a dedicated thread. I've had some people say, hey, the SQL OS service, how does that run with SQL Server? I'm like, no. That's not how it works. And they said, well, a SQL OS is one thread running in SQL Server that does all this magical work. And it's like, that's not how it works either. It's actually infused into the program. And when I show you some call stacks later, you're going to see that. And it's based on the principle of having many data structures. Data structures for workers, tasks, queues, you name it. Inside the code, it does much manipulation, a list of data structures. So therefore, that's why it's important to be partitioned by CPU and NUMA. Otherwise, if you didn't do that, you wouldn't be scalable. It is definitely an abstraction layer. So it is, in effect, the API for the SQL development team, the actual SQL engine team. They use the SQL OS API to interface with the operating system. You do not have the SQL engine QP developers, storage engine developers directly writing code to go directly to wait for single object or virtual alloc or those APIs. They use SQL OS layers to do that. It is RDBMS independent. Okay, this is something that's also a little bit of a myth. The SQL OS DLLs that you see there don't even know what a database is. I actually went and searched in the source code before I did this talk. You cannot find the word database in the SQL OS source code at all. And in fact, if you didn't know this, SQL OS powers SSRS behind the scenes for some Windows and .NET functionality. It's very scalable. As I talked about, it's been NUMA aware from its very inception. And in fact, they had the foresight when they built it back in 2005, when NUMA was just coming out, that we should go take advantage of this technology because when it does come out, it's going to be important for us to run really well on it. It's very small and optimized as well. As I said, just a couple of DLLs. And those guys always thought about supportability and instrumentation. They were always my champions to go get the right tracing, debugging, and instrumentation we needed for the product. And it itself is powered by Windows APIs. There is no hidden code in SQL OS. If you think there's some super special secret thing we do in there that you couldn't do yourself, that's not true. Well, maybe that's a little bit true, but the APIs are all public APIs. And you'll see when I'm showing you some of the stacks what that might actually look like. So how do we kind of get to this point? Just a quick little history. When you're older, you like to kind of reminisce back in the old days. So from those time ranges, SQL 4x and 6x, we use a concept called the data server semaphore. And that was a way for us to control threads within SQL Server to make sure it didn't run out of control. A very, very basic design. We translated that in 7 and 2000 to something called user mode scheduling, or UMS. That was the next evolution of this. Beware that the Windows API set has something called UMS, user mode scheduling. That's not the same thing. But we had something called UMS. And then in 2005 is when the SQL OS team came along and introduced this new concept called SQL OS, and that's what we use today for the product. So why did we do this? I actually, as part of this, sent an email off to Slava Oaks. I kind of consider him like the father of SQL OS. I said, why did you do this thing? I mean, why did you build this abstraction layer and everything? And it's very interesting what he came back with. This was all based on research by Michael Stonebreaker, and I've got a reference in here to his paper from the ACM papers. He wrote a paper about how to do proper operating system support for a relational database system, all the things you would need to consider. And so Slava and them built it based on reading this paper. And the whole concept was they want to minimize the operating system from preempting threads, because they found if they relied on the operating system to do that, they could not scale for a proper database application. The operating system doesn't know best when to run our threads when we're holding critical resources, like latches and locks, and using the buffer pool, and so forth. So the scheduling system was all based on this paper, this concept. And then we said, well, if we're going to do scheduling, why not do everything else? Why not make memory abstractions, I/O abstractions, everything else, so that the SQL engine team could just have a nice, smooth layer to access SQL OS? And so that's kind of the concept. And then here's a quote from Slava. Basically, either the operating system has to provide this, or we need to do this ourselves. And the decision was made that we weren't going to tailor Windows specifically for SQL in this case. We were going to go write this layer, but using the Windows API as this construct. So it's going to ramp it up a little bit here. It's going to a little bit more technical now than what I've just been doing. This sounds a little fluff maybe so far. Let's kind of show you. So here's Windows OS. Before SQL 2012, the SQL Server XE was 62 megabytes. Did you realize how big that thing was when you saw it on your drive? That's actually really large for an executable, especially for your server. Did you know in 2012 it's now 190K? You're like, well, where'd the rest of it go? I'll show you. So SQL DK DLL, that's where SQL OS is implemented. That's only 2 megabyte. SQL OS is only 2 megabyte. All the power of running this thing fits into a single DLL of 2 megabyte in size. And SQL Server and SQL DK talk to each other. I'll talk a little bit about that later. Now, inside SQL OS is all this stuff. Monitors, completion ports, scheduling services, memory services, NUMA, CLR hosting, XML, you name it, it's got everything. And I'm going to talk today mostly focusing on monitors and scheduling services and a little bit about memory. Now, as it turns out, to be completely clear about what we have in factual, there's also a small DLL called SQL OS DLL. It's used for a very special reason, that it can actually trap all threads that come into the to SQL Server. It knows when a thread's been created. We have to hook that up for what we call hosting services. So we use a nifty little technique where in our DLL main code for SQL OS DLL, you can get notified of any thread that's attaching and do something about it. And so that's what that code's for. So that really kind of compromised the SQL OS system. Now, in 2012, you have something called SQL min.dll. That's about 30 megabytes. There's half of the number that you saw earlier. Things like Checkpoint, Lazy Writer, Lock Monitor, those services are the ones that are inside that DLL. There's a bunch of others. Today, we are not going to focus on those concepts. Lazy writing, checkpointing, lock monitor, those are database concepts. And SQL OS doesn't know about them. Now, I'm going to briefly mention some of those, like Lazy Writer a little bit, because it's kind of hard to do a pure SQL OS talk unless you bring in SQL Server into the picture. You also have SQL Lang DLL, where things like the query processor and execution and other facilities go. That's also about 30 meg. Now I got the picture together, right? I have my 60 meg. I kind of have about 60 meg between the two of those. So effectively what we've done is we've broken up SQL Server into multiple DLLs now. So the XE still has some code in it, and it actually talks to SQL OS, and then other DLLs as well. And then to fit the picture in there, if you're wondering, .NET is also hosted inside SQL Server, okay, the .NET CLR. It actually interacts with SQL Lang and SQL OS together to do what we call .NET hosting. So that's how we support the actual SQL CLR processing that you're allowed to do and run .NET code in SQL Server. Okay, so let's do this. Let's stop for a second. And what is a Bob Ward presentation without WinBag? Now you're wondering, what is WinBag? WinBag is what we affectionately call WinDBG, or the Windows Debugger. So if the Windows Debugger team is listening to this recording, I apologize. We didn't mean to knock WinBag, but everybody internally kind of calls it WinBag. And XE stands for X event. So let's take a second here. Somebody in the front said, "Are you going to run the debugger?" And I'm like, "Of course I'm going to run the debugger." So this is, I've just attached to SQL Server. I'm going to use a command here, a debugger command. Bang is for exclamation mark, unique stack. That allows me to dump out all the call stacks in the engine but remove all the duplicate ones and just show me one of the duplicates, okay? Because idle workers inside SQL-OS, I'm going to talk about that concept, have the same stack signature. So why show that 100 times? Just show it to me once. So what I'm doing right now, by the way, you can do when you leave here. I'm using public symbols to do this. So I'm not doing anything that you couldn't do yourself. So if I scroll up here and look at this, let me just go pick one that you might be familiar with. Let's go up here. Aha! Lazy Writer. That sounds familiar to you, maybe of you. So notice here that this DLL right here, that is something you see, and anytime you have a thread in a debugger, you'll always see that from the kernel 32. The next function is what we call the thread entry point. And you'll notice that's from SQLDK. So any SQL-OS DLL will always have that. I'll show that a little bit later as well. But notice here the way the sequence goes. You've got SQLDK or SQL-OS here. Then you've got that SQL min I talked about. There's Lazy Writer. And in this particular case, Lazy Writer is waiting for work to do, so it calls back SQLDK again. Now you can see the interaction between SQL-OS, which is SQLDK, SQL min, which is a DLL that SQL, the engine supports, and the OS is the thread that started it. This is not meant for you to know exactly what these symbols mean. I'm just showing you kind of the interaction of these. Now, there are other threads that you can find. This is just an idle server, right? You can find other threads that have nothing to do with SQL-OS. Let me see an example of that. Well, there should be one in here. Here's one right here. Okay? SQL-OS, that's not a SQL-OS thread, right? That's just from something else. That's to do NetBIOS support. What's interesting, though, is SQL-OS knows about that. Because of that technique I talked to you about from SQL-OS DLL, we can trap when any thread gets created, we can record it. And we do that specifically for our hosting APIs, but it's also kind of handy from the DMV perspective. You can see all thread addresses inside a DMV and SQL Server without actually using the debugger. So now you're free to go put on Twitter that Bob Ward loaded the debugger. Although I will use it again today, I promise. By the way, again, maybe if you've seen this before, if you're on a server and you don't want to kill it, just say detach, not quit. Detach first that you haven't killed SQL Server. All right, let's look a little bit at X event. So one of the things that the product team did, I thought very well, a job in SQL-OS, is add tons of X events for SQL-OS. I don't expect you to memorize this query. That's kind of a crazy join, isn't it? But there's a specific package for X event for all the SQL-OS events. So when you run this, you're going to see a list that looks like this. Actually, let me just run this first one here. Now, if you look at some of these names, you're like, what is this stuff? Whenever you see the word callback right here, that is an example of an X event where SQL-OS is calling back to the SQL Server engine because of something it recognized. We're going to show later, we talk about deadlock schedulers, how SQL-OS can detect it, but SQL Server is the one that reports it. And so this X event can be tripped by SQL-OS to report that that event's occurring. One quick tip for you on these debug events. You notice it says channel debug. Number one, not for the average user, okay? Number two, not recommended just throw in your production server whenever you want, because a lot of these events can trip hundreds of thousands of times inside the SQL-OS code in a normal running server. And then third of all, if you use the Management Studio interfaces in 2012 to look at extended events from the GUI, these events don't show up by default. When you go to the channel option there, the debug ones are checked off by default. I guess they just want to steer you away from them. So you got to make sure if you don't see these, go in and check that checkbox to actually view them. There's other really interesting things in here, though. If you really wanted to get into this, you literally could go in here and do an event based on when node affinity had changed, for example. So if somehow somebody done dynamic affinity, which I'm going to show you, you could actually trace and see who did it and when did it actually happen. Okay. The demos will be kind of a little more livelier as I move along. I'm just kind of getting you primed, right? Okay. Let's get into the heart of SQL-OS scheduling. I kind of like the time I'm doing here. I've got till 2:45, right? Is that right? Okay, good. We got to get to the whole thing, I think, then. All right. I told you I'd really go through the OS stuff pretty quickly. But again, if it's something that kind of went over you a little bit, please come up and we'll talk about it. So SQL-OS scheduling is the heart of everything that SQL-OS does. It's the most
the biggest piece of software in that 2 megabyte DLL that they created, because it's the most important part of scaling SQL Server correctly. So let's talk about SQLOS schedulers concept first. Number one, this is the logical CPU for SQLOS. Okay, if you think about what is a logical CPU for SQL Server, think in terms of a scheduler. And it's really important to think of that terms when you're looking at DMVs and various diagnostic output, because we always think in terms of schedulers when we're trying to affinitize or think about where we're going to run our threads. It provides a method to allow threads to be assigned to CPU. Okay? Now we're going to talk about shortly here the difference between a scheduler being actually affixed to an actual hardware CPU or logical CPU versus a scheduler kind of being virtually affixed to one, and it can actually run somewhere else. It is the mechanism that allows for this non-preemptive scalable scheduling that we do. And I've got some pretty interesting diagrams to show you how non-preemption actually works in terms of the operating system in SQLOS. It's aligned by NUMA nodes. So when we start up SQL Server, SQLOS, and we look at the NUMA nodes on the system, we partition our schedulers by these nodes. And you're going to see shortly here, we're going to try to do what we can to make sure when we schedule work to stay on a node, because that promotes local memory access and scalability. But schedulers also provide a mechanism to actually affinitize your work by NUMAs or by CPUs within a node. Now, if you've looked at SQL Server and you've ever looked at the error log or you looked at some of the DMVs, you're probably wondering, what? I don't have a node. It's my laptop, right? But by default, if you don't have NUMA, that means you have one node. Okay? Now, there's an exception to that for DAC, for dedicated admin connection, that has a second node. We'll talk about that a little bit. But for all intents and purposes, if you get onto a SQL Server and you see node 0, that doesn't mean you have NUMA. That's all. If that's all you have is node 0, that means that SQLOS is just, that's the default to consider everything in terms of a node. And then if you want to go see information about this, you would look at DMO schedulers. There's information in the error log. We have specific X event entries. Some of those a little bit kind of crazy. And then we have ring buffer entries. And I'm going to show you towards the end of the presentation some examples of what these ring buffer entries actually look like. So I love to do little crude diagrams to kind of visually show what I'm talking about here. So bear with my crude diagram. But SQLOS schedulers with NUMA kind of work this way by default. Consider a scenario where you have hardware, where you have 2 nodes with 4 logical CPUs on each node. That's the basics here, okay? Notice I went 0 to 3, 4 to 7. I didn't do it reversed for you. I should have probably done that, but I didn't do it that way. I just noticed that actually when I was putting this together. Now think about SQLOS. It actually, as I said, aligns itself with nodes. What you'll see down the bottom down here is not the word CPU, but SCH for scheduler. So we create, in this particular case, we've detected there are 8 CPUs. We're going to create a scheduler to match the number of those CPUs. However, when we run work in SQLOS on this node, node 0, or on this node, node 1, we will affinitize by default to that hardware node, but we'll allow it to run on any CPU. Okay? Let me make sure I repeat that again. By default, if you don't do anything, and you have this configuration, SQL Server, when it runs a thread on one of these, that's associated with these schedulers, will run it on this node and make sure it stays there. That's why I've got that part of the drawing. But it can run on any CPU on that node. Okay? That's why I was telling you by default that schedulers are not actually fixed to a hardware CPU by default out of the gate. Does that make sense? Okay. Now, let's bring affinity into the play here, because it seems like every time I talk about SQLOS or NUMA, everybody wants to know about affinity. Okay, so affinity allows us to force tasks to run on specific nodes or CPUs and make sure it stays on that node or CPU. It does not require a restart, though. And I've got a demo to show you in a second. That's what we call a dynamic affinity. I'm going to talk a little later about something called a permanent task, a task that starts up, that runs forever. Those tasks don't move if you change affinity until you restart the server. But an actual running task that's running code can change its affinity before it completes. And I'll show you what that looks like in a task manager demo in a second. If you want to actually use dynamic affinity, you should use alter server configuration that comes with SQL Server to do it. I talk a little bit later in the talk about why SPconfigure is not an option you want to do anymore. And then there's an option called auto, which is the default, which says just what I showed in that diagram. Any CPU you have on your NUMA node, run on that node. Now, here's a concept that's going to be hard to kind of grasp. When you set dynamic affinity and you use it, effectively what you're doing is you're turning off a scheduler. So if you say, I want to affinitize node 0, but I've got two nodes, I've got node 0, node 1, what you're saying is turn node 1 off. Turn the schedulers on node 1 off and don't let any work happen on there, okay? Except for your permanent task, which can't move. And then max worker threads are actually unaffected. The reason we do that is that we're ramping up the worker pool for a given set of schedulers takes some effort. So if you're turning a set of schedulers offline by using affinity, we're not going to just go get rid of all those threads. We're going to leave the worker pool there idle so that when you put it back online, they're just available to us. We don't want to have to go through the exercise of ramping up the worker pool again. Now, Resource Governor, I've got a demo for that as well, is a little different. You now in 2012 can do affinity per pool, and you don't have to take the schedulers offline. So using Alter Server Configuration is all about changing schedulers online and offline, but Resource Governor allows you to affinitize without doing that. So let's add some affinity to this diagram. If you were to first say affinitize node 0, effectively what you're doing is this. You run schedulers from node 0 on any CPU on node 0. You still cannot run on node 1, but you take node 1 offline. Now, what happens is, and you're going to see a demo of this, any work that's happening over here, let's see, well, sorry, any work that's happening on node 1 that was running is going to get moved to node 0, okay, while it's running. Any permanent tasks like lazy write or anything like that, that's going to stay on node 1 until you restart. But usually, those don't consume a lot of CPU cycles. So that's probably usually okay, plus the fact that we don't have a design to say, hey, let's go shut down a permanent task and restart it because it's just running forever. Now, if you affinitize for specific CPUs, say in this particular case 1, 3, 6, and 7, now what we do is we turn off specific schedulers on these nodes and say don't run work there anymore, move their work to other schedulers that are online, and you affinitize with specific CPUs. So if your task is set to run on scheduler 1, you are going to run on hardware CPU 1. That's the concept. And if you were running on scheduler 0, which if it happened to be running on CPU 0, is going to get moved to either scheduler 1 or scheduler 3 on this node. Does that make sense? That's how we do dynamic affinity. So I'm going to talk more about SQL schedulers, and then I'm going to do a demonstration. So for OS support, SQL 2008 R2 is processor group aware, which means we've written APIs to detect and understand you have multiple processor groups. So we can therefore support more than 64. If you're running SQL 2005 or 2008, they are not processor group aware. And I told you earlier about a possible condition where you might get put on a processor group you didn't want to be on. Like again, if you had a processor group with 64 and 32, Windows may put you on the one with only 32. So there's an article I've got a link for that you can take some action to avoid that problem. Prior to SQL 2012, we noticed when we were running on versions of Windows, older versions of Windows, that Node 0 was more heavily used than Node 1 by the operating system. So what we did is a little bit of a clever thing. We said, when we start up, we're going to swap nodes. We're going to make our Node 0 to be hardware Node 1, okay, and our Node 1 to be hardware Node 0, because we might actually add more work to Node 0. I know that sounds kind of crazy, but that's what we used to do. We used to swap nodes with the hardware, between our scheduling and the hardware. We don't do that anymore at SQL 2012, because what we detected is that in the more recent operating systems, 2008 R2 and 2012, that the OS had made changes. We don't need to do that anymore. So when I show you some of these processor masks in error logs, for example, and you're looking at an older error log, you're going to see it looks reversed. And you're going to say, why is it reversed? I thought on my system it looks different. And the explanation would be node swapping. And then we also support hot add CPU support. So if you do hot add CPUs, that's why dynamic affinity is so needed, is that you can bring a scheduler online that's associated with those hot add CPUs. Scheduling, okay, that's the key here. We can decide to change thread affinity on the fly. Those tasks, by the way, are not like some wait for. It's a while loop. It's just a tight while loop, doing set at x, equals at x plus 1. That's all it does. But because we're scheduling in SQL OS, we can change affinity before it's actually completed its work. So that's how dynamic affinity actually works. Okay, that was kind of a Wasn't bad. It was a little showy. I've had fun putting it together. I want to show you something about the error log, though. If you make dynamic affinity changes in SQL Server, we will tell you in the error log you're doing that. Notice the mask changes here. Let me do it this way. So I was making changes. Notice that like a node 0, remember I took it offline? Notice it says 0 now. Or for node 0, node 1, remember I used a CPU mask? It changed it to 3F both ways. So if you took 3F and put in that binary arithmetic I showed you, that would map to the specific CPUs I affinitized to. So if people are making changes dynamically, you can actually see what you changed it to, and what SQL Server will recognize them as. Any questions about that? I will stop and take a question. You guys are a great audience. You didn't ask any questions. Yes, sir.
Does it use Windows to change the affinity?
The question is, does it use Windows to change affinity? And the answer is yes. There is a Windows API call to change your affinity of a thread. So we actually change affinity. And the key is, since SQLOS is doing the scheduling, our threads go through a scheduling cycle and say, should I change my affinity? And that's what we do. The actual thread changes its own affinity. Next question.
You mentioned Resource Governor.
Resource Governor.
It doesn't work the same way. Are you going to go into more detail?
I'm going to show you a demo of that. So thanks for asking about Resource Governor. Yes, sir.
When it changes to the other node,
Yes.
does it copy blocks from memory?
So the question is that if you change to the NUMA node, does it copy locks from memory? And the answer is no. So you might be accessing remote memory, right? For memory it currently has. But if it has to allocate new memory because of the way NUMA works, it would allocate new memory on the other node. One last question, and we'll move on. One last question, we'll move on.
Is the old I/O versus CPU affinity?
We will talk about IO affinity later in the talk. Okay, let me move on. You guys are a really patient audience. You didn't ask questions until I told you to. I'm really impressed. Wish my sons would behave that way. You saw a glimpse of them on my screen there, so they'll probably listen to this. You know, I thought about this. They'll probably get on YouTube or something and listen to this. So, okay, let's move on. Let's talk about SQLOS tasks. So a task is a unit of work. And in the end, you know what it comes down to? A task is a function pointer. It's not a thread. Inside SQLOS, a task is an actual function pointer to do something, some code. And it has certain properties. I already mentioned a permanent task, runs forever. Non-preemptive, those are ones that play in our sandbox. Preemptive, they don't play in our sandbox. I'll talk about what that means later. They're put into a queue for workers to process, and they're actually assigned to schedulers based on a fairly sophisticated algorithm, which we're going to get into. And then you can look at the examples of how you can see tasks, DMOS tasks, waiting tasks, X-event, and schedulers. Now here's some examples just to kind of make it real for you. Permanent tasks that are preemptive, that don't play in our sandbox, are things like scheduler monitor, which, as you notice here, is a specific SQLOS SQL DK piece of code. And by the way, I'm not revealing secrets here. You can see these from public symbols yourself. I showed you some of those in the dump, right? System health monitor thread. If you look at permanent non-preemptive task, Lazy Rider is a good example of one of those, and something called an idle task, which we'll talk about later. And then what you're more familiar with is, what about my queries? So what I call user tasks that are non-preemptive are things like TDS events, tabular data stream events, like logins, queries, RPC, batches, things of that nature. So I'll warn you, you got to wrap your head on this slide, okay? It took me a while to put this slide together, to wrap my head around it. So if tasks are the work we have to go do, and we're going to get to who actually does the work for them, if tasks are the actual work, the code to go run, how do we assign them? Because I told you that we'll assign them to nodes and to CPUs based on various algorithms. So here's how it works. The SQLOS API inside the engine supports a preferred scheduler assignment. So you can say, I want to run on this scheduler. If you don't specify it, we will use the current node you're on, and we'll use a load balancing algorithm. If there is a preferred scheduler you specified, but we detect there might be a load imbalance, we will not let you specify your scheduler. We will actually go use load balancing within the node. Now, load imbalance, this is a rough calculation, is scheduled within a node. A given scheduler has 20% more tasks than the average across all of them. It's a rough calculation, but that's generally what we kind of try to do. Load balancing says this: go assign a task to the scheduler that has the least number of tasks. That's the simple idea. You're in a line, right, at the grocery store. You try to find that line with the least number of people. That's what we try to do. You're going to find sometimes getting in that line is not a good idea. We're not perfect. We don't write this code to spend more time balancing than running. If we did that, we wouldn't be performant. So that's why sometimes you can... So please, if you come up with a workload and say, it's off by a couple of tasks, that's probably going to happen. I probably create a workload the same way. If it's way off, that might be a significant problem. And again, permanent tasks like LazyWriter and so forth, they're assigned on a round-robin basis. One of the reasons we decided to do it that way is they don't generally chew up a lot of CPU all the time. So it doesn't really matter that we use load balancing, just use round-robin. And by the way, older algorithms of SQL Server used round-robin techniques. But we now try to use more of a load balancing technique. Now, what about SQL Server itself? Is there something special we do to run your user tasks? We do. We support a concept called affinity for I/O completion ports. That is a concept by SQL OS that is bound to like a TCP port. Okay? And if you don't affinitize, we'll just round robin through these ports. So if you have a machine with one node, it doesn't matter. But if you have a machine with 2 nodes, we'll have an I/O completion port for each node. And we'll just round robin back and forth for these ports. So if you happen to connect in TCP and we pick the I/O completion port for node 0, that's where you're going to be. You're going to be on node 0. Now, so you can assign ports to nodes through Config Manager. You can actually affinitize multiple TCP ports. You can pick port 1 over here, port 2 over here, and affinitize these on different nodes if you'd like. And DMExec connections shows that affinity. There's actually a column here to see the actual affinity of your actual connections. So the node you choose from that port, the node that we choose for you from that port, that becomes your preferred node for that SQL connection. And the scheduler of the node is chosen based on the load balancing algorithm. Okay? Unless we use affinity. This becomes now the preferred scheduler for tasks for that connection. So when you connect to SQL Server, we're going to try to go run tasks for your connection on the scheduler we chose based on that algorithm. Now, preferred scheduler is overridden, though, if we see an imbalance. So even if you connected on a given node and we chose scheduler 5 or something, and we come in and run a query, and we notice there's an imbalance from scheduler 5, we may switch you to a different scheduler to try to make balancing more correct. A warning here, parallel queries operate a little differently. Bob Dorr has a really, really good blog that he pointed out. You're going to find in my reference section in the back, it's all Bob Dorr. Robert Dorr, with all his blog posts he's done on NUMA, he's like the NUMA guru. He's got a comment about how parallel queries can operate just a little differently in this algorithm. So Resource Governor offers an alternative to this. Number 1, with Resource Governor, you don't need multiple ports. And this is a 2012 feature. Okay? Before 2012, you had the ability to use Resource Governor to throttle CPU. Now you can affinitize CPUs. So consider this scenario. You've got 2 nodes, and you each got 2 ports. Okay? I/O completion ports. 1 TCP port. Okay? You've got 2 Resource Governor pools, the Mavericks and the Lakers. Hey, we beat them. Surprised me. So they're affinitized per node. So the Mavericks are on node 0, the Lakers on node 1. Okay? When the Mavericks connect, because of round robin, they could be put on either I/O port. But because we affinitize them, they will run their work on node 0. Okay? The Lakers could have the same thing happen. They can show up to either I/O port, but they'll be redirected to node 1. Now I've affinitized all my work for the Mavericks on node 0 and all my work for the Lakers on node 1. And I didn't have to create multiple TCP ports or do any configuration with Config Manager. Let's look at a demo. Oh, let me point out here that you can also affinitize per CPU with Resource Governor, and we now support something called a cap on percent executed. Let's go look at a demo of that. Just to hold me honest here, when's the break? How much time do we have?
14 minutes.
14 minutes. Wow. Okay. Wow. Okay. All right. We're going to try to rock and roll here. Okay. I'm back to auto now, just so we're clear on this. Let me get this demo up and running. Okay. Still running this guy. One thing I didn't mention here, I didn't show you in the last demo that when I changed affinity, you can go back to those DMVs and see the online scheduler mask. You'll see the change. The CPU scheduler mask will retain the same, but the online scheduler mask will change based on your affinity changes. So let's just run the resource governor demo. Okay. Let's bring up my steps here. So let me just show you briefly the script, just so you can kind of feel for what this is. This is not hard to do. Oops. Slow response from, okay, whoa. Slow response from the terminal machine. Okay. Go here, here. All right. Setup. So basically, I just set up login and passwords. I create pools and work groups. Here's the key. The key is affinity. Right here. Oh yeah, I need to keep forgetting to do that. So here's the new syntax for 2012, where you can actually specify, let me specify a specific node for my pool. So that's what I've set up here. Let's try to go run it. So let's kick off the Mavericks. We'll run them. And we'll go look at Task Manager, and you'll see, remember that node 0, right? You see the workload going there. Node 0 is kicking in. Let me go then run the Lakers. And now the workload's kicking in as well. So by that simple exercise, and all I did, by the way, since I used Resource Governor, I just logged in with those accounts and it ran a CPU-intensive workload on each account. Now I've affinitized on either node with my app, and I didn't do any TCP port changes. But what I think is, I think the Mavs are better than the Lakers. That's just a personal opinion. For those of you Laker fans out there, I'm sorry, but that's just me. So what I can do is, I can do this. I can say, they're better than the Lakers. I'm going to cap the Lakers at 50%. So when I run this, dynamically on the fly, you're going to see node 1 change its behavior. So because I capped them, because I just said I don't like those guys, you see now that node 0 is just cranking along, but node 1 over here is now capped. It's a little less than 50% here, because O-stress is also sucking up some resources, but still you see the whole concept. So I can use Resource Governor to affinitize for my apps without doing port affinity, and the switching between I/O ports is not costing me anything. I'm not using foreign memory by doing that. Yes, sir, you have a question?
Can you overload nodes where you put more than one pool?
Sure. Yeah, you can affinitize any pool on any node you want, but be careful when you're doing that, right? Okay. Let me stop these workloads. Oh yeah, they're over here. And if you don't think the Mavs are better than the Lakers, you might be right. But we can debate that maybe after the talk today. Okay, let me get back to the session here. 8 minutes before break, before you start getting really restless, right? 10 minutes. Okay, thank you, 10 minutes. Let's talk about workers. So task is a function pointer. That's the code to run. A worker is what actually does the work. Okay? So I want you to think of it that way. Task being the code, a worker is the horse behind it making it happen. So they're bound to a Windows thread to do this, except for lightweight pooling, which we're not going to get into. That's a fiber. I do not recommend this. I do not recommend this. That's like a warning for you. Do not use lightweight pooling. Anyways, they're bound to a Windows thread. That's how they do the work. They're divided into pools associated with schedulers. And if you want to know how it kind of works, they read from a queue to execute the tasks. I'm going to keep ratcheting up until I show assembly code up here or something, right? Promise? Will you do it? All right, let's get back to this discussion. So this is a really important point. We're not re-entering our code. When we switch between worker threads, we don't save the state of a worker thread, literally, and take that same Windows thread and run some other task. A worker thread is bound to a task till it finishes its operation. And permanent tasks never complete. Like Lazy Rider starts up and just runs forever. So that worker is bound to that task for the life cycle of the server. And they stay bound to the workers stay bound to their thread until we trim the worker pool. And as you've seen, they can move schedulers based on dynamic affinity. Pretty neat. And then here's some information you can see about their DMVs. I have an actual DMV query to show you a breakdown of workers, threads, and tasks all in one join, and how we can actually see it in the debugger. So here's Bob's rude and crude diagram. So here's my worker pool for a scheduler. And in my scheduler, I have a work queue, something called a runnable queue, and my running worker. And remember, I'm going to allow only one running worker per scheduler. So right now, worker 0 is running on this scheduler. So a task comes in to do some work. I take a worker and bind it to it from this work queue. And if I have long queue times, I see the infamous thread pool wait. So if I've got to wait a long time on that work queue to get my worker bound to it, that's what thread pool wait means. Now, what happens is that we decide we can run, so we first go to something called a runnable queue, but we're not really running yet. We're still kind of waiting, actually. In this particular case, worker 0 is running, worker run is in the runnable queue, and his state is runnable from the task point of view. If you look at DMOS tasks, you'd see runnable. You'd even see this state inside DMExec requests. Now, when worker 0 is done, it goes back to the pool, it's finished with its task. Now worker 1 can now run its task. That is the basics and the most simplest form of how we do this. A task comes in, we bind to it, we put them in the runnable queue, and then you start running. Now for Resource Governor, it would take like an entire talk to describe how that works. But what happens is we actually have multiple runnable queues for Resource Governor. And we put them in something called percentiles. And that's why when you set up throttling, we put you in a certain percentile queue and put others in front of you depending on the CPU percentages you specified. So that's how we control Resource Governor. We put you in runnable queues, and then we even further control how much time you're going to get to this running state. So I thought this is a very helpful diagram for people to understand how it works between SQL OS and Windows. Imagine a world where we don't have SQL OS, but we have a bunch of threads in SQL Server. Over here in what's called the ready and running state for Windows, I have 4 threads that they simply just switch between each other. Windows is preemptively switching these based on time slices. Okay? Over here, I have other threads that are typically waiting on a timeout value. Okay? Some sort of wait for a timeout. If you wait for a timeout, Windows has to check all the time to see, should I wake you up and put you over in this state to run? Okay? So that's the way it would work if we're not using SQL OS. What if you're using SQL OS? It looks a little bit more like this. Folks on the runnable queue are waiting, literally from a Windows perspective, in a wait state. And you also might have people waiting on things, timers and resources. Timer is like waiting on a time, like Lazy Rider waits every 5 seconds. And resources are like waiting on a lock or a latch or something. The key is that we use infinite waits in SQL OS. So Windows doesn't have to worry about us. Windows has no idea what is going on. These guys are just waiting. I don't have to worry about them. Over here, I have my one running SQL OS thread now. Now, I might have on this CPU other threads, right? A condition in a specific situation called preemptive for SQL OS we have. It could be one of those threads, or it could be just some other thread running on the operating system. But notice the difference, how more efficient this is. This is kind of the heart of why we made this change in SQL OS. We're more efficient with the operating system. There's only 2 threads in this particular case to go back and forth to try to go switch between each other, okay? And everybody else is in this wait state. So when Windows looks at this, it only has to make a decision on these guys, not on these guys. One thread at a time on a given scheduler. That is the heart of what we've created when we mean we're going to control the scheduling with Windows. Okay, so let's talk about how SQL OS executes threads. So this might really blow your mind. This is like 700 level maybe. But if you were to write a multi-threaded program, you would use an API potentially called Create Remote Thread EX, and you provide a function pointer. When does baseball start again? Who said they had? Somebody said they hate baseball? Did I just hear that? Oh, sorry. Man, I hate function pointer. Okay. As long as you don't hate baseball. So then you'd run your code there. In SQL Server, SQL OS, we do it different. We always have a function pointer called Scheduler Manager Thread Entry Point. That is the function pointer for every SQL OS worker thread. And then what happens is, inside our code, we're going to just run almost forever until we get rid of this thread. We're going to bind the worker, we're going to run a task, and then we're going to go back and wait for the next one to work. So a lot of people write threads where they just run a function and they just finish. our worker threads start up, and then they just kind of run forever waiting on work to do. So let me show you a DMV I have. You might find this interesting to see this. And by the way, again, no secrets there. This is all public symbol available. I'm not going to use my machine in Texas anymore. I'm going to use this machine. Now, I created a query for you here to look at. This is a fairly sophisticated join. I don't expect you to memorize this, and we're not going to go over every single piece of the command. But what it's doing is, it's joining together threads, workers, and tasks, all in the perspective of SQL OS to see a complete perspective of it. And when you run this, this is what you get back. You get back over here, this is the important point. Per scheduler, I see workers, okay? I can see workers that have nothing to do. And those are the ones that have command of null. All right? In the cases where I have a command and a status, that's my binding over to even the request DMV to see, am I bound to do some actual work? And you notice these are the permanent tasks. Okay? Like, for example, you might recognize that one. I keep harping on lazy writer. There's lazy writer, right? Bound to a worker. Now, I even have a user task right here. There's my select. That is the select running the DMV. Okay? It's the only one in this list actually as a user task running. So, I thought you might find this interesting. Can you, I've had this question like a million times actually, can I go into SQL Server and tell what thread this is and go into the debugger and match the thread in the debugger with the thread actually in a DMV? And you can. So, if you know here for lazy writer, it is thread ID 6480. Because I don't calculate in hex like just in my head, maybe some do, I'm going to do it in hex first. 6480 is 1950. 1950. So I'm going to go into the debugger, and I'm going to attach again. Okay? Now I'm going to run this command, and I think I've got this in the notes, so you don't have to memorize this. Tilde tilde 19, bracket, this is just easy to memorize, right? 150. What that says is, use an actual thread ID to show the stack. And if I hit K here, sure enough, I get lazy writer. Now would be the time for you to applaud. So I got a funny story for just real quick. When I first started speaking, like many, many years ago, I asked the late, great Ken Henderson, I said, how do I wow an audience? He said, dude, just pull a debugger up and show something like this, and you're going to just get great ratings from your talk. So that's why, no, honestly, I thought it would be kind of cool for you to see. You can see the thread IDs, and now you can match them up to something you actually see here in a debugger, and that's lazy writer. So I'm going to detach here. And we'll go back now. So you might find that DMV interesting. Go play with that a little bit. When you're actually running a workload, you can run the DMV again and actually see more user tasks pop up and see and line them up with actual workers and their thread addresses that go with them. And if you think about this, you might ask yourself, well, why, was anybody going to do that? Well, the actual SQL developers did it all the time. That's why they wrote so much of this DMV and instrumentation into the server, is that they wanted to make themselves more efficient to not have to use the debugger to go debug their own code. That's why they put a lot of this information into the DMVs. Okay, what happens if I have the simple diagram, right? Runnable queue, running, all sounds nice. But is there more to it? Well, there is. Number one, you are not allowed to run all the time while running your task. In other words, you cannot hog the scheduler. That is a no-no in the SQL OS system. Therefore, at some point, you have to yield to someone else. Okay? If you don't, you might hang the scheduler. We'll talk about a scenario where that looks like later. You may need to wait for a resource, like a lock or a latch or I/O. I call that a natural yield. You're not voluntarily yielding. You're just saying, I need to go wait for something. But in the SQL OS world, that ends up being a yield. You also may need to wait based on a time, like lazy writer wanting to run every second. The way that works is lazy writer calls SQL OS and says, hey, wake me up in a second. And so that's waiting on a time. Remember, though, in our premise, We always wait on infinite. We don't wait on a timeout for Windows. So SQL OS is going to be responsible for checking to make sure to wake up Lazy Rider in that second time period. So if you've been running for some time and you have not naturally yielded, you've not waited, you have to voluntarily yield. Okay? That is the basis of cooperative multitasking in SQL OS. When SQL Server makes that decision to do this, it marks the infamous SOS schedule yield wait type. So I think I did wait type talks here a couple of years ago at PASS. That's what that wait type means. When you voluntarily yield, you mark the wait type, you go into the SQL OS system to switch. When you change from a running state to a waiting state or a voluntary yielding state, that is called switching. You must always attempt to switch. If you don't attempt to switch, it's going to have bad consequences. So what happens, though, if no one else is runnable? And you switch. You were running. You were doing great. You're hogging the CPU. You said, OK, I'm going to be a nice guy. I'm going to voluntarily yield. I'm going to give somebody else a chance. And you go look in line in the queues, and there's nobody else to run. You probably could say to yourself, why do I even have to check? I'll just keep running all the time. We can let you run again, but you got to do a couple things for us first, and I'll explain why. You can't starve the runnable guys. We just described that. Here's the problem. Since we don't use wait timeouts in Windows, and we're going to talk about async I/O in a second, you've got to do what we call idle processing. You first need to make sure that no async I/O has completed for someone who's posted it. Okay, you've got to check on async I/O, because if you don't, nobody's going to process it. We'll talk about that in a second. You must wake up somebody waiting on what we call a timer. So think about the Lazy Rider scenario. Lazy Rider says, wake me up in a second, but it doesn't use wait for single object with a timeout value. It does infinite. Well, who's going to wake it up? It can't wake itself up. So the person that's running on the scheduler, when he decides to switch, he says, hey, let me go see if anybody needs to wake up. So it's a housekeeping operation he performs. In addition, if anybody who has had a resource that now acquired it, we got to move them to the runnable list, like waiting on a latch or a lock or something like that. Now, that sounds interesting. That's how we achieve this magic, right, behind the scenes. But you may ask yourself, hey, wait a minute, who's going to wake up Lazy Rider if no one's running? What if nobody's running? How do you do that? These SQL OS guys were not dumb. They thought of this. So what you'll see is on every scheduler is something called an idle task. A specific task is created for every schedule, and all it does is sit there in the idle processing state. So when nothing is going on, the idle task says, oh, I'll go check all this stuff and do it. And that's its job. It performs what I call idle processing when no one else is available to do it. So we usually use the workers to do the idle processing, and the idle task is doing it when no one's actually running. Yeah, go ahead.
Why is the IO completion worker not reused for that purpose?
For what purpose?
For the idle task purposes.
The idle task worker, the question is that why isn't a worker reused for that
Why is
purpose?
the IO completion worker not reused for that purpose?
So the question is, why isn't the IO completion worker? Do you mean the IO port completion worker?
Yeah, I mean, there's always a worker for that as well.
Yeah, the IO completion worker port task, its primary job in the world is to do what? Is to wait on IO completions. So it can perform idle processing too. So it has that capability. Okay, but if IO completion, there's one per port. But if IO completion is actually waiting on a natural wait, there's always a chicken and egg here. You'll always find one of the threads that has to go do something or wait on something. So the idle processor doesn't normally have to do a lot of this, but in some cases it has to. Okay. I'm sorry, what's the question? Who spawns the idle task? Who calls the idle task? The idle task is always available to run. We create idle tasks when we start up the system. Each scheduler gets an idle task created for it when you first start SQL Server. So doesn't have to be specially called. Okay.
If nobody is running, why should Lazy Rider wake up?
So the question is that if no one's running, why should Lazy Rider wake up? That would be like a whole other talk to do, right? I'm not making fun of you. I'm just saying it's a whole other discussion. By the way, here's a scenario for you. You're going to see when we talk about async I/O, when SQL Server goes and reads a database page, it's not the one waiting for the I/O. So if we don't have idle do it, then we might have I/O never gets completed. Okay? So it's not just about timers. It's a series of housekeeping tasks that have to be done. Remember, the reason we have to do this is because we are in control of the scheduling of our threads, not Windows. You have a question over there?
Are you going to go over why a schedule would not yield?
Yes. The question is, are we going to go over why a schedule would not yield? And we are going to talk about that. Hey, just a quick check. I'm going to what time? 4:30. Okay, is that right? 4:30. Okay, good. I can go later. I just keep going. Just stay here all day long. I don't fly till tomorrow, so I don't care. I'll stay as long as you want. So, okay. There's no sports events I can think of tonight I need to be watching anyways. My teams aren't doing very well. Well, I guess the Mavericks are doing pretty well. So the election's over, so that's all done with. So what does preemptive mean? So I talked about the fact that we're non-preemptive in our scheduling. But don't we have these scenarios where we could be preemptive? Now, let's be clear about something. When we're running in the SQLS scheduling world, we're in that running state. Effectively, we are in a preemptive possibility state, right? Windows could preempt it for some other thread on our CPU. But here's the key. He's not going to preempt it for any of our SQLOS threads because they're all in a runnable state, the runnable queue waits, or in waiter states. That's the key to the system. Now, there are some scenarios, though, we have found where we're running something inside SQL Server or SQLS even, and we don't have control of what the code might do. Okay? So, consider these examples. SQL Server to authenticate has to make a call to a Windows routine called lookup account SID, which has to hit a domain controller. Okay? So if that gets delayed, all right, and you're one of these running tasks on a scheduler, what might happen? What was your question earlier? Non-yielding. There you go. There's the answer. You won't be yielding, right? Because you're in the middle of lookup account SID. Does that routine have any idea about SQLOS scheduling? No. It's in Windows. It doesn't know what we're doing, right? What about an extended store procedure that you would write, even though we've deprecated that now? If you wrote an XProc and you just wrote your own code, you don't know anything about SQLOS, you might not be yielding. And then the other one is the kicker. What about log file growth, right? We're zeroing that log file. Write file gather doesn't know anything about that either, right? So in these states, if we let them play in our sandbox, there's going to be trouble. That's the way I kind of look at it. If we let those guys play in that sandbox in our scheduling system, and we don't do something special here, there's going to be a problem. So what we have is we have a scenario where SQLOS allows a worker to temporarily leave the system, and we call that preemptive mode, right? We call it preemptive mode because now Windows has control. We don't have any more control of this worker thread. So when I showed you that diagram earlier about thread X sitting on there, that thread X could be a preemptive SQL thread doing one of these operations. Windows now has full control to preempt this thread, right? It's not going to be part of our system. Affinity doesn't change, and what happens is it can come back to non-preemptive when it's done with this task, and it just moves to the runnable queue on the same scheduler it was on. That's how it works. Now, the symptom for you, or the key is, how do I know these guys are in the state? Well, first of all, on the DMV I just showed you, there's a column that says is preemptive. You can actually see is it in preemptive state. In addition, when SQL Server will take a worker and it needs to go to a preemptive mode, it actually uses a new wait type called preemptive something. Maybe you've seen this. We've shipped it since 2008. We've added it on there based on CSS feedback. One thing to call out here, and I called it out in my wait types talk, whenever you see in DMXEC request that wait type, the status will not be suspended. It will be running. That's because we don't know in these scenarios whether you're truly running or not. I'm not sure that I agreed with that decision personally. I kind of thought suspended would be better. But anyways, I want you to know if you see those, that's what that state means. Okay. I told you we have to do this idle processing work, right? One of the things to do is to wake up timers and wake up people that have just acquired resources. What about asynchronous I/O in SQL Server? How does that work? Well, first of all, SQL Server uses async I/O to read database pages. I don't have, I don't know if you remember my slide that I did on latching, okay? But the whole concept is that you go off and use a latching concept to wait for your I/O to finish for a buffer, right? So what happens is that if SQL Server is waiting on this latch, who's going to process the I/O? If the I/O finishes, there's no thread available to do that. So SQLOS provides a mechanism for threads to process async I/O. So SQL Server will use SQLOS to post the I/O. We don't call the actual APIs. We let SQLOS do that work. And we give them something called a completion routine, which is a function pointer, which understands SQL Server, like buffers and things of that nature. And then during a scheduling switch or idle processing, SQLOS will check the status of async I/O and say, oh, if it's finished, I'll go call that completion routine, right? So they give us a function pointer that they know. We don't even know what it does. It's just a function for us to call. We know, though, when the async I/O is actually processed. So what that means is a really odd situation. A given worker can post the async IO, but some other worker can actually be the one in its thread stack to process it for you. Because again, it's a cooperative system. If we don't do this, somebody may never process it. But it also could be the idle task that actually does that. So what happens is that SQLOS, here's another data structure again, it maintains a list of these IO requests. You can see these yourself by looking at this DMV. DM IO pending IO requests. That's a mouthful. So if you look at that DMV at any point in time, that is a pending list of all async IOs that have been processed that SQLOS knows about. Now, one thing that might throw you a little bit is we use a concept called IO completion ports for this, but we also use it for networking, okay, for disk and disk IO, for networking and disk IO. So in that DMV, you're going to see a network type in there. That's not a disk IO. That has to do with simply networking concepts. So my point to you is that when customers tell me about this DMV and go, hey, I'm running this thing, and there's a bunch of stuff just flying in and out of it, I'm like, that's normal. That's IO getting processed coming in and out of the system. If you were to see a given IO request show up in there for long periods of time, you will probably see something like an IO stall warning, or maybe heavy IO latch problems or something like that. So if you think you're getting massive IO delays, you could look at this DMV and see actually which IOs are the ones causing the delay. Okay, so that is really, in a nutshell, SQLOS scheduling. I mean, we could have done an entire pre-con seminar on SQLOS scheduling, right? It could have been that massive to go through. I want to stop, though, and take a second and see if you have any questions. Do you get the concept of what we're doing, how we're doing our scheduling? Have I helped overcome any myths you have about this magic that was going on? Question there first. How much time does a thread have before it dies? Oh, it yields? So we try to, okay, so that's a good question, actually. So, and now that I think about it, I don't know how much I actually put into the talk. I think maybe in non-yielding I might talk a little more about it, but let's just address it now. So it is a voluntary system, right? Okay? Which means that the developers are the ones responsible for doing it. Okay? Okay? So, there's various techniques that they use, I'll be frank with you, to do this yielding. In some cases, they know and can recognize in their code, they don't see a flow of a natural yielding point. Okay? Here's an example. Compilation. Query compilation. A lot of times they're going to go through there. Now, sometimes they may have to wait on a memory grant or something. That's a natural yield wait. But a lot of times they think, oh, I can run this for a long period of time. How about an in clause or something, right? I don't have to yield anybody. So they put natural points in the code to say, I think I need to yield. We do heavy performance analysis in our code to determine some of that. Some of the developers got smarter, though. Some of them said, hey, if I need to go scan a table that has database pages that's in the million range, well, maybe not the million range, but it's large and they're all in memory, there's no yielding point there, right? I'll just go scan to this table in memory, and I don't have to yield any. So they have created what they call a smart yielding concept, where they do it based on a time quantum. So normally you want to have like a 4 millisecond time quantum shift. That's usually when you want to do your time slicing. So they've actually put in algorithms to help make that happen. SQLOS actually has some primitives that help the developers make some of those decisions. But it is not a consistent methodology where in the code we have some sort of thread checking, hey, is this guy yielded? Let's go make him yield. We don't do anything like that. It's up to each piece of code running in the engine to make this decision to do the voluntary yielding, which is why you're going to see here shortly, you may not yield right. Sometimes we make a mistake, right? Does that answer your question? I'm sorry? Milliseconds. Yeah. I'm sorry? I don't remember what quantum boost is, Adam. You'll have to ask me later, because that one I don't remember. Yes?
It seems like there's a lot of security concerns that come into play here with all these function pointers. Does SQLOS check the values that it's getting and making sure that they haven't been tampered with?
Security checks for function pointers. I think that would all be based, that's probably beyond the scope of what we're doing right now. I mean, I could probably spend 15 minutes trying to think about what you're asking for. But that's all internal to the engine. And those function pointers are not coming, the function pointers themselves don't come from like a packet, network packet or something. That's like a hard-coded pointer. It's not, the function pointer itself is not something that shows up on the net from a client and we take that pointer and then throw it into the engine. That's not how that works. It's a hard-coded pointer that we know about. The difference is that in the code for the engine, we'll take a packet, like a login packet, and we'll say, this login packet represents this hard-coded function pointer name. It's like a lookup table, and go call that function. It's not dynamic based on some user request or something. Does that make sense? Yes?
So then if the
So, that's a great question. We're going to talk more about that in the non-yielding slide I have. We actually figured that out. We actually looked for worker set trimming of our process, and we have some smarts here to say that's not a not yielding situation because of that. So, one more question, then we'll move on.
The parallelism, how it will be handled among the workers when, for example, the query will be given to, say, 10 CPUs. How does the scheduler see which part is done?
Well, our assignment of a task or a query is not based on CPU utilization. It's based on what schedulers have the least amount of tasks. It's not based on CPU utilization. We don't say, hey, this scheduler has 90% CPU, but this one has 5, so go use that one. We don't base it on CPUs. We base it on the number of tasks that are assigned to each scheduler. Okay, let me move on. We will definitely still have time for questions. So let's talk about monitoring and services. We have something, so the SQLOS guys, again, they're thinking, being proactive. They're like, look, we have all these tasks, we have this scheduling system, let's put a special task that we run for anybody using SQLOS to monitor resources, okay? It's called the Resource Monitor. Its primary job is to check for memory conditions in the process being hosted with it. Number one, it wants to know for Windows, are we in a low physical memory state, okay? And if you want to know the magic behind how we make that happen, here's one of the public APIs we use. Query Memory Resource Notification. Anybody can call this in your process. And if you do this, you're asking Windows, am I in a low physical memory state? Okay? There are two ways to do this. One, you can use a function pointer where Windows can call your function and tell you when there's low memory, or you can query it yourself using this. We choose to do it this way. So Resource Monitor is running all the time, and every time it runs, it goes and says, let me go make this function call to ask Windows, am I low or high in physical memory? In addition, specifically for 32-bit situations, we need to check to see, are there any problems with the virtual address space? Are we low on the virtual address space? And also, are we low on virtual memory itself? Perhaps maybe a page file misconfiguration. And then, we need to know the state of available memory from the process we're hosting, which is SQL Server. So we're also checking for the state of SQL Server's own internal memory. Is it under pressure? And then last, we need to know about working set trims, right? We actually make function calls in our code in Windows to say, is our working set being heavily trimmed? And if so, we start giving you warnings and make certain decisions based on that. Now, this system has a complete architecture to do notifications and indicators based on all of this. That would be an entire memory talk to do, right? And the way that works is, you can read more information about it from this hyperlink that we have, where it shows you from the Resource Monitor ring buffer, what do the various states mean? But just in a nutshell, if you think about what we might do, if we detect low physical memory, what do you think that we'll do as a resource monitor? What should we do? So let's be clear. You're all right. But from a generic point of view, Resource Monitor says we need to shrink memory. That's its generic message. So it is a series of callback routines in SQL Server, function pointers again, that it says, I need to go call those functions and say, you got to go shrink memory, which is going to end up calling Lazy Writer and various other SQL Server routines to make decisions for SQL Server itself. So Resource Monitor is independent. It doesn't know about Lazy Writer, but it knows it needs to go tell the guy it's hosting, you need to go shrink memory because Windows has told me so. Okay? The other thing it does is check for stalled IOs. So that's where that message comes from. But actually, as it turns out, we call back into SQL Server to actually report the message. In addition, we have this memory broker system. The memory broker system is actually supported by SQLOS itself. It's a generic memory broker system. The users of that system you may have seen in SQL Server, procedure cache, compile, and query memory. Theoretically, anybody in SQL Engine could use the broker system. It's a generic system that they built. But those are the three users of it inside the other DLLs I mentioned. And the state of Resource Monitor is exposed to NOAA ring buffers, but only when it detects there's a conditional change that it needs to report. And you can see some of the information that it's operating on in these various DMVs, in DM memory status. There's also an X event for the ring buffer event. So for example, if Resource Monitor detected there was low physical memory, you could look at DMOS process memory and there's a flag there to say, hey, I detected low physical memory. Now, it's a volatile flag. The next time that we run and think it's high, we'll flip that back again. If you want to use to see the state of it in a historical record, you could query the ring buffers, or there's an X event for the ring buffer itself, so you could just save it off if you wanted to. And the last thing I thought you might find interesting is that Resource Monitor is responsible for idle detection of the system, of SQL Server. So in SQL Express and the new thing we have called SQL LocalDB, we're probably running on a low-powered machine, maybe a laptop. And so what we do is pretty clever. We can detect when everything's kind of idle, and we power down. We actually trim workers. We power various things down to a level that we won't consume CPU, so you don't lose battery life on your airplane. But that's the idea. So Resource Monitor is the one that supports doing that kind of detection. In addition, we thought it was important in SQL OS to detect the health of scheduling. Okay? Resource Monitor is all about resources. Schedule Monitor is all about scheduling. Both of these monitors, what they are actual tasks in SQL OS. They're actually spawned up by SQL OS to do their work. So it's an independent monitor for the health of scheduling. We don't want to rely on the workers to see if they're healthy, obviously, right? Especially a guy who's not yielding. So we need somebody else to do that. What we have is we have one per node. It's a permanent preemptive task. Does anybody know why Scheduler Monitor must be a preemptive task based on everything I've told you? Yeah, it's got to be able to get through a situation that might be a non-yielding scenario. If it's running on a schedule that's not yielding, it doesn't get to run. It could get starved, right? So it's got to go do the work, and that's why it runs in a preemptive mode. And it runs every 5 seconds. It monitors the health of the schedule of a given node. If a schedule has a running task, a guy in that mode that's not switching, remember I said it has to switch, it detects this, it's a non-yielding scenario. If all the schedules are stuck, and there's not memory pressure, like worker set trims, that's called a deadlock scheduler scenario. I'm going to talk about these in a second. If the IO completion port for TCP, for networking, is also stuck, we also can detect that condition. That's a very severe condition because you can't connect anymore to SQL Server. We also produce a condition for that. We also can check to see if Resource Monitor itself is stuck. Why is that important? Because that's the guy responsible for telling everybody you may need to shrink your memory usage, or you can grow your memory usage. And then if any monitor detects a problem, this is where that callback mechanism comes into place. SQL OS is not the code that reports the problem, it just detects the problem. So when it detects it, it calls a function pointer in SQL Server to do the actual reporting or handle the logic of what to do. And the various state of this is exposed in a few different methods. In OS ring buffers, in Xevent ring buffers, and this is probably one you haven't seen before. Undocumented trace flag, warning, 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 warning. Okay? 8022, I'm going to show you a demo of that though. 8022 is a trace flag that can dump into the error log every 5 seconds. It checks to see, do I have a stalled scheduler? Okay? And it will dump that information into the error log. And then there's a new Xevent in 2012. When we do those callbacks for like a deadlock scheduler condition, okay, you can actually trap that with an Xevent. Okay? That's important because, as you're going to see here, we change the logic for deadlock schedulers on when we produce the stack dump, so it's important to know about that Xevent. Let's talk about a non-yielding scheduler scenario. I call it the bully. Okay? So if you have a scheduler with a worker that's not switching properly, remember we said we have to always switch, I call that a scheduler in a non-yielding state. You think of it as a running task, he doesn't have to do any waiting, but he's not playing well in our sandbox. He's being a bully. Now the victims are like the old grocery store line problem. I know you've been in this state before. You go to the grocery store, you check out, maybe it's a Walmart, right? You get like 40 lines. So you get up there and you're like, which one should I get in? Like, oh, that's the one that's got the lowest line. And you get in that line, and you think you're going to zip through, and then you discover somebody at the checkout line is like, you know, Marv, check on aisle 2, you know, go check the price for it, and you just wait forever, right? And everybody's passing you by. That's kind of what this is like. The victims of non-yielding are victims. They happen to get in the wrong line. It's not their fault, but they're delayed. And you can have a given scheduler that's not yielding and everybody else gets to run. Remember our algorithm about preferred scheduling for tasks. If you, on your preferred scheduler, happen to catch a guy in a piece of code that's not yielding well, you're kind of a victim. It's not your fault. So here's what happens. We do a callback like I mentioned. We call back into SQL Server. We say, hey, we detected one of these. And that Xevent fires right at that moment. Okay? SQL Server, after 60 seconds of this condition, if it gets called back enough times, it says, oh, have I seen after 60 seconds? I will generate message 17883, which I'll show you an example of what that looks like in a second. Then what I'll do is I will generate what's called a stack dump. You've probably seen that in the error log. But I will only do that if it's the first time for the life of the process, unless you have this trace flag on, 1262, which says dump it every time you run into it. Then you have another trace flag, 1260, that says don't ever do it. Okay? So if you want to disable it altogether, you can use 1260. If you want to say do it all the time, use 1262. If you say I only want to do it one time, then you just leave the default. Now, this is a really interesting scenario. What if there's a bully in that line that gets in there and he yields before 60 seconds? You don't know about it, right? Unless you're using that trace flag 8022. So this is another undocumented option. There's a trace flag 8000 that enables what we call quantum thieves. You like that name? Okay? What it'll do is when you turn it on, it'll dump out error log entries when it detects a quantum thief, and it turns on an X event called quantum thief. And a quantum thief is one that takes 15 seconds without yielding. So you can detect a guy doing it quicker than 60 seconds by using that. In addition, here's another symptom for you. If you have tasks or requests that are in the runnable state for long periods of time, the guy on your schedule that's running, that's a quantum thief. Okay? So sometimes you're looking at exec requests or DMO's tasks, you might see that runnable state kind of come in and out very quickly. Well, that's normal because you're just doing snapshots of DMVs. I've had scenarios where, and actual bugs in the product, where we never saw a stack dump ever. But the customers say that runnable state is actually there for a very long period of time. I actually did yesterday in a pre-con talk where I showed a demo of a problem where it looked like a temp DB latch problem. But the owner of the latch was runnable. Okay? The owner of the temp DB latch was in a runnable state, and he couldn't give it up because somebody else was running on his scheduler that was not yielding. So it looked like a perfectly normal temp DB latch problem, but it turned out to be nothing to do with temp DB. So that's that kind of scenario you might take a look at. The other thing is that we have something called a signal wait time. So when you look at DMO's wait stats and you see a signal wait time, a high wait time means it took a long time to wake a guy up to run after he waited. So if you see that, it probably means there's got to be a yielding problem. So there are other symptoms without this undocumented quantum thief thing that you can look at to see yielding problems even without seeing a stack dump. This is what one looks like. I think I grabbed this from a SQL 2008 R2 dump, and the only thing that should give you some confidence or hope is that I haven't been able to create one in 2012 yet. I could create a hack to do it, but I haven't created an actual scenario from a customer to make it happen. The thing I wanted to point out on this slide here is that if you look at this, here's the stack dump you see right here with this header, and then this is the message 17883 below it. Now notice that that message is repeated multiple times without the stack dump. That's because the stack dump happens once, but the message is repeated each time that it happens. Okay? And in there you're going to see a hex number. That is the OS thread ID of the non-yielding person on the scheduler. You could take that dump, take that thread ID, and tell exactly who it is, based on the technique I just showed you on how to line up a thread ID inside a dump. Okay, that's one condition, non-yielding schedulers. There's another condition we check called deadlock schedulers. It sounds similar, but it's actually different. Let me explain why. Got about an hour. Are you guys staying with me here? We're doing good? Okay. I'm about to lose my voice, I think, but I'll keep going. Bob, it doesn't matter, raspy talk. Just keep going until you die. Okay. What if all schedulers on the processors are not progressing with any new work? In other words, they're yielding, but their workers, remember workers run the task to completion, okay? What if everybody in the system is doing a lot of work for long periods of time, not giving up their workers, and new guys coming in cannot even get in the line? That's called deadlock schedulers. So no new task can be serviced by any scheduler in a given node. It's per node, okay? The current tasks, they're doing stuff, and they're yielding, but they're not giving up their workers, all right? So what's interesting about this scenario before I show it to you is you could have this situation occur with some schedulers and not know it. You wouldn't see an actual error message because this detection by Resource Monitor is for all schedulers in a given node because there's a Resource Monitor for each node. But I've seen a scenario where you could actually have a few schedulers in this state. If you had that, how would you know? You'd know by long thread pool waits for some tasks, okay, and the work queue count in the DMOS scheduler DMV would be greater than 0. In fact, it might get to a very high number. Does that make sense? So if you're looking at the DMVs and you see that state, first of all, it would be hard for you to connect to SQL Server without dedicated admin connection, right, with all schedules deadlocked. But if some were, you might be able to connect in. And if you could, and you saw this state, you might think, I might be in this kind of stalled scenario. But it's not a not yielding scenario. Does that make sense? And here's kind of what, well, here are the error conditions. We get quite complicated, actually. And this is a change that I detected, and I found it and didn't know until I ran and did this presentation. So prior to 2012, the same non-yielding check would occur for 60 seconds. We changed that now to 5 minutes because we found some scenarios through testing that we would get noisy problems like this if we did it every 60 seconds. I don't have the details on why that happened, but this is something I just found out. If this occurs after 5 minutes, we will produce a 1788 message if half the waiters are waiting on network I/O, async network I/O. If half of them are doing that, but they're all deadlocked, we'll print a different message than we'll do for all other conditions. And we create a stack dump based on some very interesting logic. And this is one that'll catch you. So prior to 2005, I think it's 2005, we would do debugging with the debugger, and we'd freeze the debugger by just looking at the stacks. And then you come out of it and you get a deadlock scheduler message, right? Because no work complete. So what they said is, okay, if the process is starved of CPU completely, because like using a debugger, we won't produce the message. And of course, we won't do a stack dump as well. If 50% of the waiters are in that network I/O state, we don't do a stack dump. We just print a message saying, hey, you got a bunch of guys waiting on network I/O. That's probably your problem. And then we have other complicated rules here about when to actually dump, similar to non-yielding. And then I mentioned about trace flag 8022. That could be used, by the way, on the fly, using DBCC trace with -1, trace on with -1. You can actually, on the fly, turn this thing on. I'll show you in a second. Now, what are some examples? All workers blocked, which is the most common one I've seen. Everybody's blocked on a lock or something like that, right? But a couple scenarios you might not have thought of. Like Bob Doerr loves this one. Bob Doerr will just create an infinite while loop on every worker. And he'll run like, he'll set worker threads to 255, and he'll just run a ton of them. Boom, you got this scenario. What's going on there? The workers are yielding, right? They're all yielding, but no new work can come in because they're all using up worker threads. And then here's one you haven't thought of. Maybe all workers are preemptive. I literally had a case many, many years ago where a customer was in this state because he had an extended store procedure that was a main part of his business logic, and all the workers were running that extended store procedure. And it was off doing some crazy calculation that was taking like 5 minutes. So he was running into this state because all the workers were consumed doing that and no new work could complete. This is what this looks like in a SQL error log. You get a stack dump based on the conditions I said, and then you get a slightly different message than non-yielding. No new queries assigned to this process have not been picked up by a worker thread. That's what it means, right? And you see in a particular, because it's by node, you see the node, and you get a stack dump and can go look at the stack. So, can I hang SQL Server? You were probably betting that I can. You can too. It's not complicated, but let's just show it to you. You can too. You can also hang SQL Server. News at 11. Here we go. So let's go here to demo 6. Excuse me. So let's set up the hang. Oops. Probably going to give this away. Actually, I'll tell you what I'm going to do. I'll just run this. It'll be easier. PowerShell sometimes, man, it gets frustrating to run with quotation marks. So all I'm doing is, and I'm going to fix max worker threads because otherwise I have to run too many threads to cause this. So I'm just going to set max worker threads, which is dynamic. Okay. And let me go back and what I said in the my real README here, because I want to make sure I do this right. I don't have a README. That wasn't a good idea. Okay, I think I know what to do here. I think I got the database already set up. So what I'm going to do is I'm going to go out here, and I'm going to run an update to a query. I've got a database called Are the Cowboys Mediocre? And a table called Is Romo Any Good? And I'm going to run this transaction. And then I'm going to run my repro. And I kick him off. And a big sign to me that there might be a problem is that I can't run a query. I get the nice little spinning bar. And what's going to happen is it's going to come back in timeout and say, well, I can't even do this, right? So without spending a lot of time trying to debug the problem, I'm just going to go do a dedicated admin connection. Admin, colon. Oh, yeah, it's like, whoa. Ooh, that scared me, man. Like, can I not get in? Hadn't had that happen. So I'm just going to go do a dmexec requests just to see kind of what it looks like. You might have seen this before. And if you go down here with the user, what have I got? A bunch of blocking, right? You're probably already guessing, what did he do? If you don't really know already, if you look at blocking session 71, what is 71 doing? If you look down here, he's suspended, and it's a blocking chain problem, right? It's a typical scenario. 52, so you see 52, 71's blocked by 52. You come up here, 52 is missing. What's up with that? We'll talk about that in a second. So what I'm going to do is, because it takes 5 minutes to detect the situation, I'm going to run a new query, or actually, I'm sorry, from my dedicated admin connection query, I'm going to run trace on 8022 -1. Okay? Now I'm going to come over to my error log file, and I'm going to type it out. Whoa, look at that. So now I can see already the problem starting to creep up here. So scheduler monitor is saying, I've detected some of your schedulers are in a stalled state. That's that every 5-second check that's going on. So this behavior literally will go on for 5 minutes until finally there'll be a stack dump that'll show up, right, in the error log. But I told you there's some other symptoms of this problem, if you remember. And I got dedicated admin connection up and running. What else might it look like? What about sys.dm OS schedulers? Can I look at that? If I look over here, here we go. Look at the work queue count column. See that? So, not good. Now, you could run this DMV on a healthy system and see that thing kind of fly up and down a little, pretty volatile. But if it stays in a state like that for a long period of time, that's what's going on. You've got some sort of situation where no new work can be picked up. Remember we talked about the problem, the concept of SQL-OS? Tasks go first into a queue called a work queue. All right? That counter is simply a count of the queue. Who's in the queue? How many are there? They are now waiting for a worker. What is another symptom that I can look at from a DMV at this point? Does anybody know? Adam, got it. Thread pool wait type. So if I go down here, do you see how I have some thread pool waiters? Look at their wait time duration. Pretty huge. I also want to point out to you, I had somebody contact me before on this, when you're running a massive workload on SQL Server, you're going to find some thread pool waits that are going to flash in these DMVs very quickly, right? Because we're just, we're in the process of trying to assign a worker at the point you ran the DMV. It's the wait duration you've got to look at. If that gets really extremely long, that's an indication you're running into this state of having a deadlock scheduler. So, I'm in dedicated admin connection. I said it was 52. Now does anybody know why 52 is my problem, but it doesn't show up in exec requests? It's not running. What I did is I just ran a transaction, and I stopped. So it's a session that's active with an open transaction, but it's not running an actual query. So I could kill it. Anybody want to take any guess? Does that work? Anybody know? What does exec request look like now? All freed up. So on a server that was hung, I was able to connect with the DAC, kill a task that had an open transaction, causing the world to block. He rolled back, and now I've unwedged the deadlock scheduler hang scenario. Okay. So here's the question is, why doesn't it go into a spin loop status? Did somebody ask that question? Spin loop status? So what did you mean by spin loop status? Okay, the question is that why did I kill it and that work? Is that what you're asking? Okay, so the question is, what if I killed 52 and it couldn't roll back? Then I couldn't solve the problem. And there are scenarios where a rollback doesn't work, right? Or a rollback to do something that gets in a state where you can't kill that, right? It is possible. I've seen it. This was a very simple demo just to show you that it was possible to roll this guy back. It is possible to have that happen. Okay. The question is what?
Any external process running any process on the SQL server, like light speed or anything, try to kill it and it will.
The question is, if I kill light speed or external process, it's going to go to a rollback state. Oh, it's an extended store procedure, you mean? Yeah. I mean, remember how kill works, right? Kill is a signal. It doesn't go inject itself into a thread. Kill just sets a bit that thread has to wake up and say, should I die, right? Kill is not where SQL Server injects itself into a thread and says, you will die. That's not how it works. So if you're running a piece of code that doesn't check for a kill signal, it's not going to die. In this particular case, it's a session that's not doing anything, so I can kill it. Makes sense, right? Okay. Moving on. I'm sorry, what was the question? It's past this conversation, but I would challenge you. There are scenarios where you don't want to do that. Okay, let's talk about some other SQL OS services. Let me get to your question here shortly. So first of all, SQL OS is the one that provides the base mechanism for something called ring buffers. I've had people ask me before, what's this ring buffer thing? What it effectively is it's kind of what the definition says. It's a memory list where any piece of code using it can write in a trace of information. And it does it in a ring buffer way. So each buffer, there are actually multiple buffers in this scenario. It's not just one. But the DMV exposes it as one huge list. The ring buffer type denotes the different ring buffers that are in this list. So it varies in size before it wraps over to the beginning. I don't have the exact numbers of what it looks like. And memory pressure can also affect that. And here's the cool thing for us. When you get those dump files you give us, we get a copy of the ring buffers in memory in the dump. So sometimes you'll give us a stack dump. We can go in that ring buffer and see, was there working set trim going on or other types of problems, and help diagnose a problem just from the stack dump alone. You would not be able to do that because you need private symbols to go look at the actual dump structures. But for the DMVs, you can do it. Plus, Xevent allows you to write out the buffers to a file. Extended events, which we're not going to dive into the details of extended events, but you should know that extended events is actually built inside of SQL OS. But technically, SQL OS hosts it, so they wrote Xevent in such a way that it can be separated to its own separate DLL and be hosted by other processes. But think of it effectively as being immersed in with SQL OS. And the actual engine itself is there. And the XE engine provides APIs and threads to support the whole Xevent process for SQL Server. But what's interesting is SQL OS uses those APIs too. Remember the events I showed you for thread and queue, node affinity changed, the deadlock callbacks and so forth? Those are X events produced by SQL OS calling the Xevent APIs to make that happen. And then finally, dedicated admin connection. If you didn't know the history of this, this was a CSS feedback because of what I just showed you. Customers would get into a schedule or hang scenario, and I said, hey, can't you guys create me a special port and a special little scheduler and reserve some memory for it where I can connect in backdoor into the server if it's wedged and maybe go in and do something with it? And that's what was born, this concept, dedicated admin connection. So it's got its own scheduler, its own node. You can do a lot of stuff in it, but there's some things you can't do. You can't do a parallel query. So you can't do CheckDB, or you can't do like a backup, for example. So multiple workers don't work. And then sometimes you can hang it. I've had that happen before where I'm trying with a customer system, and I need to do something that was an additional piece of work that had to go off that scheduler, and it actually hung the whole DAC process. And if you haven't used it before, you can use admin:server name for remote, admin:./ or -a through SQL command to actually use it. I want to show you a query I wrote for you that's in the scripts for ring buffers. You might find this interesting because I help you shred the XML a little bit. Not completely, but I certainly help you break out the timestamp, which a lot of people ask me how to do. Let's get rid of the Cowboys are mediocre, because they are. Worse than mediocre. Hopefully no Cowboys are listening to this thing. Doubt they would. Okay. So, what I built you for is a script to go take a look at the ring buffers, and I crack out the timestamp for you because it's all based on CPU ticks, so you can see the actual date time. Because people say, what's that timestamp thing? And so I order by that. And so if you run this, you can see the various types of ring buffer types, and I've actually broken this as an XML record. When you see ring buffer type of scheduler, that's a record of almost everything that occurs, like an idle condition state. We might be able to catch one as a switch. Like, here's a non-preemptive resume. Look at that. So this is when, inside the scheduler SQL-OS, we have detected that we need to go resume a non-preemptive runnable worker. So you can actually do tracing almost of scheduler events that are going on. And in here, these addresses, see the source and target worker? That lines up with an address from DMOS workers. Okay? The problem is you got to catch it. You might have a worker that got trimmed, so you got to be careful sometimes to look at these addresses, whether it actually lines up with a worker that's still in the system. So I thought you might find it interesting. You can go play with this a little bit and see the different types of ring buffer types. I should point out to you that some ring buffer types are not SQL-OS, like Hobbit Schema Manager. What's that thing? That's a SQL database engine concept. And so it has its own ring buffer, but it uses SQL-OS APIs to actually do the call and create a ring buffer. That's why this DMV is exposed through SQL-OS, because it doesn't know what the types are. It can just dump out all the information in it. And so if you look down here, now the interesting part is about the some of our monitors, like Scheduler Monitor, for example, that every 60 seconds will produce what's called system health information about process utilization, page faults, and working set trimming every 60 seconds. It'll also produce a record when it detects one of those conditions for yielding. And then also, in addition, Resource Monitor has some information in there. And that was the one link I provided to you guys from Bob Doerr's blog, that if you look at it, it will give you information about high physical memory, low physical memory. His blog gets into details about all these different effect types, indicators, all that information. So you notice it's got statistics on actual memories by node, because it runs on each node. That will not produce a message every time it runs. It only produces a message when it detects a state change. So if you all of a sudden went from a high physical state to a low physical state, you would see a new record show up in OS ring buffers. And again, if you're worried about, well, I don't want to just sit here and pull this and save it off to a text file, there are X events for each ring buffer type. So you could set up an X event session and save it to a file anytime we record a ring buffer. I don't recommend you do it for the scheduler one. That's really more for kind of a tracing point of view, because there's so many going on. But you might want to do it for Resource Monitor or Scheduler Monitor. And there's some other ring buffers for even connection errors and security and some of those kind of things as well from the engine. Okay. Making good time. Okay, let's briefly talk about hosting, another service that SQL-OS provides. Consider SQL NCLI for a second, the native provider for OLEDB and ODBC. That typically runs inside of your client app, right? You use the APIs, that DLL is loaded, you use it. What about link servers? What about it? The DLL for link servers is that DLL if you're using the native provider, right? So we have to load that DLL inside SQL Server. Well, that DLL likes to be a little hoggy, I'll call it, with memory. All right? Now, we want SQL Server to control memory as much as we can, SQL-OS. Therefore, we actually create a hosting system so that SQL NCLI can call back SQL-OS to get memory when it needs it. That's what the hosting system is all about. And the way we achieve that is through that thread attached process I told you about from SQL-OS DLL. The one you're probably wondering about most is CLR, SQL CLR. We're not going to do an in-depth dive into SQL CLR today. I'm just going to mention to you, though, that this hosting system is supportive of it, but it's actually through SQL Server. SQL Lang DLL is a go-between for CLR. So when you look at thread stacks inside SQL Server in the debugger, you're not going to see a direct interaction between SQL DK and CLR DLL. You're going to see SQL Lang as this go-between. And if you want to know kind of how this concept works, the CLR APIs themselves provide a hosting API. And so, for example, when CLR needs to allocate memory behind the scenes, if you use this hosting API, based on function pointers again, it will call your function to get memory. Well, in the case of SQL OS, it's going to call SQL Lang, which is going to call SQL OS to actually go get the memory it needs. That way, CLR can participate in a SQL OS system for scheduling and memory needs. Okay, speaking of memory, let's talk about it a little bit here. It, again, would take another complete half-day pre-con seminar type session to go into memory. I did a deep dive on memory back in 2008 or 9 or something like that. It was more of a comprehensive memory discussion with the SQL Server Engine and SQL OS. So I'm not going to spend, as you see here, we have like 35 minutes left. I'm not going to spend 2 hours on it. But I think enough information that you'll like to see about changes in 2012. So first of all, SQL OS is a base memory service provider. Just like scheduling, it provides API calls for SQL developers to get memory. It's a fairly complicated system. There's NUMA support. There's all these things called, in 2012, called workspaces and fragment managers and block allocators. The concepts of clerks and objects and cache stores and pools, they'll all still exist. Resource governor is all built in as well, okay, and memory brokers. So it's a complete massive system provided for the benefit of the SQL Server Database Engine. SQL 2012 changes the architecture. I actually grabbed this slide from my talk 5 years ago. I did this slide, which I was told, by the way, was very confusing when I did it. But I thought it was still a good representation of what happens. And I want you to focus on the buffer pool part because that's one of the biggest changes. So when we need cache in SQL Server, we use this buffer pool concept. The buffer pool is going to use, prior to 2012, a virtual allocator API from SQL OS to get its memory. Okay? And that ends up calling virtual alloc or ADB APIs. If backup buffers needed memory, it has its own clerk for it, but it might need single pages. Excuse me, I'm sorry, it goes directly to virtual allocator as well. But what about something like plan cache? Plan cache might need single 8K pages for part of its caching. When that happens, it's going to use a memory object and a memory clerk specific for plan cache, but it needs a single page through SQL OS. Prior to 2012, that single page allocator would call back into the buffer pool in SQL Server Engine to get that 8K page. And that is using, back to SQL OS, the virtual alloc APIs. What a crazy mess, right? But that's the system we built prior to 2012. And also, we had the concept of multi-pages. So if you needed more than 8K page, you would go to SQL OS and say, I want multiple pages, more than 8K page. So flip forward to 2012, and it looks like this. A lot cleaner. Buffer pool is now a memory clerk, and that's all it is. It's not an allocator anymore. When it needs memory, it goes into the SQL OS system and says, I need 8K pages. I need single 8K pages. Okay? When other clerks need memory, they also go into SQL OS and say, I need memory. And there is no single versus multi-page concept anymore. I just need pages. I need one page or I need multiple pages to do my work. But I don't have special allocators for that. We'll talk about why that's important in a second. So a much cleaner system, much different system, and a much better system, I think. And there's some benefits to this, which we'll talk about. And the important point here is that SQL OS doesn't know anything about that buffer pool thing anymore, or the database engine, for that matter. It just has generic interfaces for memory needs. Now, in fairness, we built this for the SQL engine, right? It's not like we built SQL OS and said, oh, we're just going to build this for anybody writing a program. We knew we had database-specific needs, so it's a generic system built for the needs specifically for a relational database multi-threaded system. Why do we make the change? We need a consistent model for memory management versus that buffer pool system I talked about and multi-page system. We wanted to get rid of this multi-page concept. Why do we want to do that? That's because we wanted max server memory to really mean max server memory. Yay! Now, to be clear, thread stacks, heap allocations from other procedures and threads and so forth, that doesn't come from max server memory, but now multi-pages do. Plus, how about resource governor? I'd like resource governor to get control of that stuff as well. And so that's now been added as well. And then, of course, we want to set up Bob for another talk. So another reason we made the change. So what's visible for you? So the DMVs and DBC memory status have removed this single-page, multi-page concept. So when you look at the DMVs, and you look at a DBC memory status, you will no longer see that, and you'll no longer see that when you see like an out-of-memory message show you the different clerk information. We've got a new tracing system in Xevent inside SQL OS. Since all the pages come from SQL OS, you can trace literally every page allocated and freed from Xevent. Yesterday in a pre-con, I did a demo where I showed a memory leak problem, and we used Xevent to show where the leak was using this technology. The error log has more information about memory models it's using. Lock pages. You no longer need a trace flag for standard edition. It comes on by default if you have the privilege set. So if the lock pages memory privilege is set and you're running standard or enterprise, we will automatically use this lock pages feature. 32-bit mem-to-leave has changed. We no longer reserve the entire address space for 32-bit systems, but that is our cap. But we don't need to reserve the entire thing anymore. AWE feature completely removed from 32-bit. It doesn't even work, even though we still use the AWE APIs to do memory management for 64-bit. And then this is a nice tip from Bob Dorr. If you're running on NUMA nodes with CPUs greater than 8, so the nodes themselves have more than 8 CPUs in the node, this trace flag might be beneficial because there's certain CMemThread classes we use for memory that are partitioned by NUMA, but this trace flag turns them into CPU partitioned, and it makes it more scalable. And then if you're on SQL 2012, you might consider applying CU3 or later. There's a couple of specific bugs that are fixed if you're using NUMA systems or column store that you might take a look at. So to briefly touch on memory nodes in NUMA, we promote local node usage. I talked about that before, and we talked about how we promote it. We try to run you on your node as much as we can, and then on that node, that's where your memory comes from. We try to avoid foreign pages. Now, foreign pages, don't think of that as just being a terrible thing. It's not like, it's tens of milliseconds slower to get access to this memory. It's a cache line miss, but it is faster than disk. But you want to avoid it. You want to take advantage of NUMA scaling by using local memory as much as possible. But if there's no available memory on a given node, we will try to go to a different node to get memory for foreign pages. That is part of the algorithm of using Windows APIs. And just because we support this system, if SQL Server goes and grabs blocks of memory, at a time, it may have to be aware of NUMA as well. So it has code in its logic to be aware of NUMA just as well as SQL OS is, because if you think about the buffer pool, it allocates large chunks of memory with virtual alloc or AWE APIs, and then it manages that for you, right? So it has to be a little bit NUMA aware to promote local node access. So here's a situation you might run into I thought you should see. One of the engineers in CSS pointed this out to me. What if you've got 2 nodes, each with 24 gig at the hardware level, and you've got max server memory at 48 gig? What if you were to take one of these nodes offline, but you didn't change max server memory? So what's going to happen is, when you get above a 24 gig type number and SQL Server needs more memory, it's going to go get it. Where's it going to get it from? It's going to go to the foreign node. So if you're going to take nodes offline, you should adjust your max server memory to account for that, to promote local memory usage, because you said go up to 48 gig, but you didn't adjust it based on the actual node configuration of your computer. That is a situation that did happen to a customer that we ran into, and they were doing benchmarking, so it was a very precise benchmark. I'm not even sure you would notice this at a normal workload level, but if you're really tuning the engine to the server, you might actually see this. Okay, let me show you cute things about memory. And then we're going to do something fun. I think I've got the fun exercise here where I'm going to do something interesting. So, yes. So let me show you, if you've not seen it before, DMOS memory clerks. Oh, okay. I thought I'd create a script, but actually I'm just going to run the query for you. DMOS memory clerks. Now, without getting into too much details with buffer pool, it gets a little bit dicey. But if you look over here, the biggest change you're going to see is the pages KB column used to say single pages KB and multiple pages KB. And people were like, what the heck does that mean? Now it's just one column, pages KB, right? And one of the differences you're going to see is buffer pool will look different, because buffer pool was an allocator and a clerk. So some of the statistics for bpool will look different in this output than they did before. But it's cleaner now. It's a cleaner environment, cleaner system. So as I promised you, you can do some tracing of memory. So with extended events here, I actually built some sessions, and the scripts are actually in there. So if I turn on this session right here, and I go watch it live, I am literally tracing the actual allocation of memory in the system. And notice that I already got some allocation from Xevent. By running an Xevent session, I was allocating memory for Xevent itself. So this would just be a complete tracing of all memory by clerk, how many pages are being used, and actually the allocator are using across the entire SQL Server system. If you're into that, you can go do that all day long. In one of the scripts I handed you, I use something called the event pairing target. The event pairing target allows you to match up a page allocated and a page freed. And if you run this right, and you think you got a leak, the ones that are showing page allocated but not page freed are your leak. And you can attach a query to it. And if you did that, you could find out what query is causing the leak. And so I had a demo in the pre-con seminar where I did this, and the cause of the leak was somebody running XP prepare XML document but not removing it. And so running that scenario using this, I proved that that was the cause of the leak. So anyways, kind of an interesting little nice instrumentation. A great example of SQL OS team saying, I don't want to run a debugger for this stuff. I'm going to instrument my own code to do that. That way I can use this technique to go find out. In fact, during the development, when they added this, they would use this to show the other SQL developers where their code was leaking. Pretty interesting. They would call them and say, we think you're leaking memory. Like, no, you're the one leaking memory. Let me show it to you. Okay. So this last little section I have here is, I call this practical advice. This is probably the section here where there's debates that'll happen, right? So I'm going to pick on Adam here in the front row. I think I made a comment a couple of years ago about max DOP or something, right? And he came up after the talk and he goes, there's no way you're right, man. Are you kidding me? You can't do that. You can't say that. You don't, I mean, in a practical world, we set max DOP of 1 and so forth. So I guess I'm not trying to pick on Adam. My warning is that this is my advice based on what I've seen. You may have a various opinion or a different opinion about it, and that's fine. It's perfectly healthy. But this is kind of my experience based on talking to customers. And you got to remember, not many customers call me and say, my server's running awesome, Bob. So this is kind of my advice based on customers who say, things are really bad. So I kind of have this feeling about it just works. I mean, they built the SQL OS system to run without you having to touch it. That was the whole idea. But you've seen things I've talked about today that gave you a little bit of a hint that maybe I should do some touching of it. But here's a couple of points for you. In the lifetime of SQL OS since 2005, the lifetime, I don't even know how many QFEs there have been for this part of the product. Probably on my hand I can count them. High quality work. And in fact, one of the things they did that's really cool, they built a special test harness and program to test SQL OS without SQL Server. Because they said, this needs to be modular without needing the engine. So they wrote a special test harness, and they felt that was a really good thing they did to speak to the quality of this. So my personal recommendation is to just for most people, just let this thing run, right? And then make adjustments as necessary. But there's some things you might consider, like what if you have multiple instances? Maybe that's where Affinity makes sense, right? To consider that, or max server memory adjustments. What about special app needs, like the resource governance scenarios you're thinking about? Maybe reporting needs, Mavericks, Lakers, that kind of thing. You're what I call a NASCAR driver. You really want a highly tuned engine. Think in terms of you driving my Ford truck versus a NASCAR. I want to let my truck just run typically, but as a NASCAR driver, you're down there really tuning the fine parts of your engine, so you might want to tweak some of this stuff. And if you have a legacy SQL with a new ROS, take a hard look at it, especially SQL 2005 or 2008 with Windows 2008 R2. If you've got more than 64 CPUs, you definitely need to pay attention to that. You might run into a problem you didn't realize. And then if you encounter a problem, certainly that's something to start taking a look at some of this stuff. But so many times I found it's an app problem or a hardware issue. It's not a config issue necessarily you need to be doing. Again, Bob's personal opinion based on my experience. What about Resource Governor as a feature? Well, you may have used it, may have not used it. The thing I want to point out is some changes they made in 2012. I've shown you some already. Affinity, I think, is a really interesting feature, right? Because until this time, you had to take schedulers, you had to affinitize and take certain schedulers online, offline to affinitize, right? Well, why not let you affinitize by your app and not have to worry about I/O port affinity, schedulers online, offline, that kind of thing. And then this true cap on CPU. So let's make sure we explain this. Prior to 2012, if you set a max CPU percentage for a given pool, and you're the only one running on a scheduler, let's say you set it to 50%, and you come to me and say, I'm getting 100%. Why? That's because the design was done that way. It was designed to be a max if you're competing with other workers. But if you're the only one running, you're not going to be a max. That's what cap is for. So that's a new feature in 2012, that if you set the cap at 50, you are really capped at 50. And that was the demo I showed you from what I provided in the demos. I capped the Lakers at 50, right? We've upped the number of pools. Memory now controls multi-page allocations because there is no such a thing because we have a new memory manager. So there's new features in Resource Governor. It's all built in SQL OS, but the SQL engine is the exposed method to access its feature set. What about using Affinity? We talked about multiple instances. You really want to tune the engine. You want to play with deciding when to affinitize. You know, based on what I just told you, you realize you could affinitize all CPUs, right? If you wanted to. And then you're actually affinitized to the hardware CPUs. You're not worried about Windows maybe switching around because we're going to affinitize those threads to the specific CPU that you're on a scheduler for. That's a possibility. What about dynamic affinity? I was mentioning to somebody, you might want to add an instance, okay, and affinitize. And with dynamic, you could do it without a computer restart, theoretically, right? You could have an instance running on your server, add a second SQL instance, use dynamic affinity to affinitize both of them, and you never restarted the actual computer itself. And then if you had a given problem with a NUMA node maybe or something like that has a bank of processors, you could potentially take it offline to avoid using those. Although, as I pointed out, SQL might use the memory of that node if we don't have enough memory in the current node we're running on. Definitely use alter server set configuration as your option to do this. SP configures is deprecated, and it only supports 64 CPUs. And then there's more options for alter server like node affinity, which SP configure doesn't actually support. And then, of course, Resource Governor Affinity allows you to affinitize your apps. Big, big warning. Do not use Windows Task Manager to affinitize SQL Server.exe. Okay? You could break SQL Server actually to do that. And actually, I think I've seen some comments in the code where our affinity logic would fail. Like if you affinitize with Windows differently when we try to affinitize, some of our APIs would actually fail. I don't even know what that error message looks like in the error log, but that's a scenario you could run into. Okay, let's talk about just briefly I/O affinity. Somebody asked it earlier in their talk. I/O affinity is not a SQL OS concept. That is a SQL Server database concept because that is affinitizing LazyWriter. Okay? So when you talk about I/O affinity, SQL OS knows nothing about that. There is no option or configuration for the SQL OS DLL to do that. That's a SQL Server configuration. And the way that works is that is the SQL Server engine making a decision on where to put LazyWriter on multiple nodes or multiple CPUs. Soft NUMA. This is a topic maybe you've heard of before and you're wondering about what it is and should you use it. Well, try to tell you whether you should use it, maybe a tougher one for me, but let me tell you what problems you might run into. It only applies to scheduling, not to memory nodes. I got my laptop, I've got soft NUMA configured right now. So if you look at DMOS nodes, you see 2 of them. If you do DMOS memory nodes, you see 1 of them. So we don't split up memory because there is no memory node. You just have one memory bus, so we can't do that. Now, does that cause a problem? Not necessarily, but I want to make sure you understand when you go look at the DMVs that you're wondering, why did soft NUMA not create me 2 memory nodes? You could use it to subdivide hardware NUMA, actually, if you think about it. You could take it and take hardware NUMA nodes and use soft NUMA to even divide the CPUs even to a further NUMA, like sub-NUMA set if you wanted to. I'll leave it up to you guys to figure out why you would want to do that. Connection affinity, I/O completion ports are honored. So for soft NUMA, we would build 2 I/O completion ports, and you could affinitize if you wanted to. However, I/O affinity for LazyWriter is not honored. In fact, there's something in the documentation in older docs where we mistakenly say that it is. It's easy to see. Set up soft NUMA and go see how many LazyWriters you have. You got 1 of them, not multiple. And more importantly, dynamic affinity does not work. I've tried it. Tried it in the scenario I have. And Management Studio will not show you nodes. That's because Management Studio is querying the memory nodes DMV in combination with OS nodes to show you how many nodes you have. And so it's only going to show you 1 node. So that's just some points about soft NUMA. Do you have enough worker threads? Please, let's not get into an hour debate on this one, because maybe you have a very strong opinion about this. But let me just tell you what I think. Number one, let me tell you the formula, because people ask about this. SQL-OS decides this based on number of logical CPUs on the platform, and I've got the formulas listed up here. And there's a chart in the books online. So, for example, I believe on my 8-processor one, I have, 512, what's the algorithm there? 512 plus 16 times 4, whatever that is, right? That's what I have on my 8-proc laptop, right? So the question is though, is that good enough for you? Well, first of all, if you see high thread pool weights, do not panic to say, I need to just go expand worker threads by 1,000. Why? Because you just may be prolonging the problem. So I guess my contention is that tune your workload first. Tune your app first. Make sure you don't have a lot of high blocking problems or long-running queries that can be tuned. Because if you're in that state and you just bump up more worker threads, you're just creating more blocking or long-running query scenarios for your server. So this question has come up, well, who cares? Can't I just put a 10,000 in there? Why do I care about that, right? Well, first of all, each of those threads require memory. So having 10,000 idle worker threads is actually chewing up after a while a lot of memory that each thread requires. And SQL Server is going to trim those idle threads after 15 minutes. We start trimming back the worker pool a little bit, and we also trim based on memory pressure. So growing the worker pool, okay, and trimming it back actually can be an expensive operation if it's happening all the time. So again, you could put a large number in there, but there could be a small cost to it that you have to consider, especially if you're a NASCAR driver tuning your workload. So here at the end of this document, I have several blog posts. Half of these are written by Bob Doerr, my colleague Robert Doerr. He is absolutely the NUMA guru. Nobody knows NUMA better than Bob Doerr. In fact, nobody knows SQL-OS on my team better than Bob. I kind of wish I had him here on stage with me, because it would have been really a delight for you to hear him. If you think I made your head spin today, he makes my head spin in my office all the time. So if you think it was tough today, he's like 1,000 level. So let's stop. We got about 15 minutes left. I really like the timing of this. I thought I would be actually over a little bit. Let's stop and we have 15 minutes for questions. Let's do as many as we can here in 15 minutes. What do you have? Please say it loudly. I'll repeat it, but go ahead. Yes, sir.
One question. As you have said, you are doing cooperative scheduling inside.
Okay, I'm sorry. Can you hold just a second? I see a lot of people leaving. Let me just make a comment before you guys leave real quick. Evaluations, okay? Evaluations, if you haven't heard already, they're online. I take evaluations very seriously. So please fill them out for me, okay? And I think they're giving away a Surface or something like that. But I read your comments all the time. So what I'll do here is we'll end our session right now, and then I'll stay here for questions for all of you guys that want to remain as much as you can. So thank you so much for your time. Thank you for your patience. Appreciate it. Okay. Questions? Go ahead. Can you ask your question again? Can you? He's got a microphone right here you can use.
Check.
You have said that you are doing cooperative scheduling inside SQL Server.
Cooperative multitasking, yes, sir.
How you can prevent that those threads inside SQL Server are preemptive scheduled by the Windows OS?
You can't. So the question is that how do you prevent Windows from preempting your threads doing the system? The point is that you can't, but it doesn't matter, because Windows is not preempting the other SQL-OS threads because they're all waiting. So it can preempt your thread, all right? And if there's no other threads on your CPU, who is it going to preempt it to? You. You're just going to keep running back and forth. It's going to look at your time slice and say you can just keep going. Now there might be other threads like preemptive threads from SQL-OS or other threads from Windows that it could preempt to. But the point is we've minimized how many threads get preempted because our threads are controlled by us. Does that make sense?
Yes, thanks.
Okay, you bet. Other questions? Yes.
Older documentation that used to say, like, you turn on affinity mask, then you have to also make sure these are not shining.
The older documentation said if you turn on affinity mask, you need to also be careful with affinity. That still applies, even with our affinity. But I haven't really looked into that. I don't know. I think there's some documentation from Doerr on that about those complexities. I'm sorry, you have a...
One caveat on that.
Sure.
Don't do that on SQL Express.
Yeah. Yeah. So I think Bob's got some blogs about that mixture, and you're right, that still applies. It's no different even with our current design. It's not just because SP configures alter server that doesn't matter. It does matter. Next question. We'll come back. Yes.
You mentioned about powering down the worker thread.
Yeah.
Was that related just to SQL Express?
Yep.
Oh, okay.
Idle detection is only done on SQL Express or LocalDB. We do not do it on Standard or Enterprise Edition. Yes, sir. Parallel queries, yeah. The question is about parallel query scheduling. Each parallel worker is a task. So remember my task system? They're all separate tasks. They have their own coordination between them. You may have seen CX packet weights, right? So that's orthogonal to SQL OS. So SQL OS does not coordinate parallel workers. Those are just separate tasks SQL OS is trying to schedule. The engine coordinates the parallel workers itself with this CX packet exchange operations. So that's independent of SQL OS. Yeah. Yes, sir. The question is, how does MaxDOP affect NUMA? MaxDOP is an engine property for how many parallel workers to run per operator. Okay? Those, again, are tasks. And I mentioned to you that our preferred task system I talked about, there's a slight twinge with parallel workers. And in the deck, there's a link for you to go read about that. But it's basically, we have a similar system for those parallel tasks SQL Engine does on where to go set those for certain schedulers. Yes? So the question is about hyperthreading, is it okay now? So personal opinion and experience. So I don't remember the exact name of the chipset, but Intel came out with a change in their chipset several years ago. And the Halem, thank you. And I have experienced since that time no issues with hyperthreading, even for high workloads for customers that call us. You may have a different experience, but even myself in my own testing and when customers that call us, I have not seen issues with it. Yeah, I think they've improved that, but I don't know the details. Next question. Yes, sir. So the question is that if you use an I/O completion port on a NUMA node that is overloaded, it's because of slowdown in connection, not for the completion port processing. The completion port worker is preemptive. So you don't have to worry about that. Yes? Yeah? Backup buffers. Backup buffers are included in Mac server memory because it is all part of the entire SQL OS allocation system now. So it's all included. Next question. The question is that what I'm sorry? Yeah. The question is that would I consider doing any tuning differently for warehouse workloads versus OLTP workloads? Parallel queries might be a factor in the warehouse scenario, right? I don't think so really, except for maybe if you want to run a mixture, right? So like if you have a warehouse workload where you want to affinitize that on a given node, and then maybe on another node, maybe put other types of work on there that are not, like you might want to prioritize your querying in the warehouse area, maybe, I don't know. That's the only thing I can think of. Right. That's what I'm saying. You might want to take a given node on a multi-system and say, you guys just should run on this node now, and nobody runs on this node, and we'll all go run over here. That's a possibility. That Affinity gives you that option. Yes. I want to make sure I get both sides.
Are you aware of any improvements in Windows Server 2012 and SQL Server 2012 as far as SQL OS, scheduling, memory management?
Am I aware of any improvements in Windows Server 2012 with SQL 2012 scheduling? Man, I should have researched that. Off the top of my head, I'm trying to remember if there's any specific processor groups we're adding to R2. We don't support REFS yet. Although that's not a SQL OS concept. I don't think so. I don't know if a different API call we make or anything special there. Maybe it's possible that there's different behavior because of an improvement in 2012, but I'm not aware of an additional API call we make in that version of the OS versus 2008 R2. That might be a nice email question to send me, by the way, on that one, and I could try to get you some more information. Yes?
Which things stole the database when it's in the recovery mode after SQL Service 35 or something?
which things stall a database in recovery after restarting SQL Server?
Yeah, with the full recovery mode and it's in
Yeah.
recovery for a long
Okay,
time.
so the question is that why would something become recovery? That's kind of independent of SQL OS. But just real quickly, I did a part of my pre-con seminar about VLF fragmentation can cause that. So that's the typical reason I go look for. So long-running transaction. I mean, recovery is a total independent from our SQL OS discussion, but that's what I usually look for. So I/O processing. Over here, I want to make sure I'm balanced. I'm NUMA balanced. Yes.
Do we have to consider anything different with respect to virtualization?
Ah, that's a really good question. So what about Hyper-V and virtualization? SQL OS doesn't have specific special code for that, but I think you do. But you need to know this. For 2012, I just thought of something. It is NUMA aware. So guests are NUMA aware now. And there's more CPUs supported. So there's a consideration there that I think SQL OS could operate potentially better in that environment now with Node Affinity in Hyper-Vs in 2012 before that. So that's definitely a consideration. Next question. Anything else? Yes, sir.
Non-yielding IOCP listener, and does it mean IO problem?
So non-yielding IOCP listener. Remember I talked about IO completion ports, right? So one thing Resource Monitor does is it detects to see is the IO completion port worker stuck. That is a very severe problem for your server. It means no connections can happen on that node because IO completion can't run. Why does that happen? Number one, working set trim that I've seen. Most of the time when we've caught it stuck in the dumps, it's buried inside a Windows API call. I saw a case 2 weeks ago where that problem happened because the customer had run out of page file. He'd run out of virtual memory on the entire computer. And the IO completion port was trying to allocate memory from Windows, and it was stuck. So that is a very severe problem. And you'll get a stack dump for it. And usually when we go look at that stack dump, you can do it with public symbols, you can see it stuck in some Windows call. That's not a SQL OS problem. That's not even a SQL problem. It's a Windows or system issue. Well, it depends on the problem. So for example, if we think it's working set trim, maybe you should use locked pages. Or take a look and see why maybe you're low in physical memory. If it's an out of virtual memory problem, in this customer's case, they had a memory leak from another program in the box, and their page file was misconfigured. Slow I/O is another. Well, let's be clear about slow I/O, okay? Because I've had this question come up. I/O completion ports for network are not disk I/O related, okay? It is only for networks. But slow disk I/O could cause some other problem on the system that could cause that thread to get stuck. But it is not I/O completion ports. When you see that in the stack dump, that is not a disk I/O issue indicator, okay? That worker is not for disk I/O. It's for network I/O. Yes. I'll come back. Yes. The question is SQL OS being used in SQL Server.exe or other places? I know that I just bombarded you with like 70 slides. Way back on my earlier slide, I said SSRS uses it. So reporting service uses it as well. That's the only other process today that uses it. It's not using AS or agent or anything else. Yeah. No, just in RS right now. Just today. Yes?
I also see lazy writer as out of free buffers. Also, right before,
Lazy writer out of free buffers you see. Right before this problem?
yeah, before the non-yielding.
Could be out of memory. It could be your problem. But it would be more of a physical memory problem. I/O completion port, by the way, does not require SQL Server memory to do its work. It doesn't need SQL Server. So if SQL Server is like out of stolen memory or something, that's not going to cause that problem. But a physical memory problem might cause it. Or virtual memory in the box. Yes, sir.
Is SQL OS sensitive to virtualization? Does it behave differently?
Well, I think it's what he was asking me earlier, sir, about virtualization. So it doesn't behave differently, but you may consider some tuning with it differently. So, for example, it's not NUMA aware before 2012, Windows 2012, but it is now with 2012, Windows. And, you know, I guess you have to think about this very carefully. If you've got multiple Hyper-Vs running in a box, would you consider Affinity maybe? Possibly.
I was thinking specifically different kinds of virtualization, so Hyper-V versus VMware versus virtual.
We run on both of them. We actually, by the way, one thing SQL OS does do, by the way, it does detect if it's in a hypervisor environment, and it prints it in the error log.
That's exactly
Yeah.
what I was asking.
You can see that. Now, I think we also dump out the manufacturer information. I have to go double check that or not. It might say VMware versus Microsoft or something of that nature. So we do detect it, but we don't do any special logic to say, oh, you're on VMware, let's go do something different versus Hyper-V. We don't do that.
That's exactly why I asked.
Yeah, we don't do that.
When a parallel query is run, and one of the workers completes on a scheduler early,
Yeah.
how long does it delay before it gets off the scheduler? Does it delay a little bit? Keep it-
The question is, for a parallel worker, if a worker is finished, what happens for scheduling? So I think I'll answer it this way. Workers, for parallel queries, first of all, workers don't know they're running parallel queries. They're just running a task, okay? It's the tasks that matter. So if a task for part of a parallel operator is finished, it depends on the coordination with the other task for that operator. That's why you see CX packet wait, right? So sometimes you'll have CX packet wait types for a given task because it's done, waiting for the other guys to finish. So in that case, when you see a CX packet wait type, that worker is still waiting on that task. It's not finished yet. When a worker is done with a task, whether it's parallel or not, the worker goes back to the pool, the task is finished. So for a parallel scenario, we would not be finished with a task until all the parallel tasks are done.
Oh, but there's still a yield that it gets off the scheduler to let something else go.
Oh, it can yield.
Okay.
Okay, but in the CX packet wait, it's a natural yield
Okay.
because it's a wait.
But is there any logic for leaving it on there just a little bit longer to see if all the rest of them complete really quick?
No, but that's not a SQLOS decision. SQLOS just knows you waited. See, SQLOS doesn't even know CX packet wait. It just says, oh, you're waiting on a resource. And then if you get that resource, which is a CX packet resource, I'll let you run again. So there's no SQLOS decisions in that logic. That's all up to the engine to decide. Does that make sense? Boy, what a loaded question. So let me answer more SQLOS questions. That's like totally independent of SQLOS, your question about parallel workers. I wish it had come to my wait type talk like a couple of years ago. I'm just kidding. But let's talk afterwards at the clinic about that, because I can talk all day long about CX packet waits. Other SQLOS questions that you have? So there's a lot of people still left here. Okay, sorry.
A NUMA question.
NUMA.
Putting host bus adapters on each PCI bus for each NUMA node.
I have no idea. To be honest with you, man, I haven't played enough with configurations, and I'm not copping out, but I'm telling you, a better team to answer that is a CAT team. And they're in the clinic. Those guys deal with that kind of configuration all day long with our biggest customers. Probably to help with affinity, with like port affinity or TCP port affinity, but I'm not sure.
So like IO wouldn't have to move from one to another.
Well, that's all a hardware thing at that point, right? So SQLOS doesn't even know that. It's going to use it. It's not going to look at that to make its determinations. Put it that. Yes, sir. What I'm sorry, can you speak louder? Lock partitioning? Yes. Yeah, that's independent of SQLOS. It doesn't know about lock partitioning. But you're right. That's a SQL. That's not a SQLOS thing. That's an engine thing. But there are issues with lock partitioning in that scenario you're talking about. We've seen that actually. Yes. In ring buffers? Yeah. You mean like the connectivity ring buffer specifically? I'd have to go look at the details of the connectivity ring buffer. I think there's information there about what API failed, for example. But I don't know what connection context information's in there. I'd have to go look at it. It's that, I'm not trying to cop it on SQLOS, but SQLOS is independent of that. It's all about the connectivity manager. Any other questions? I think we're about wrapped it up. Yes, sir. Soft NUMA is a way for you to add NUMA nodes to a system that doesn't have hardware NUMA. No. We'll just partition the schedules by those nodes. You're not going to add schedulers. The schedulers are done by the number of CPUs, not by NUMA. But we'll align the schedulers to the nodes. Does that make sense? Okay. Thank you, guys. Again.